Okay, Ooh, got that going. Make sure it's not gonna auto zoom out on me this time. Stay. Okay, starting our last chapter now. Our last chapter, what was our last chapter all about?
First law. Second Law of Thermodynamics.
Or no, what's this last chapter all about? Because you all went and read the book like I asked you.
Yeah, it's about
So what's it about?
Entropy.
Entropy. The second law of thermodynamics, entropy, we'll see a bunch of logically equivalent ways of stating this second law of thermodynamics. But one of the ways that it's often stated is entropy in the universe either stays constant or increases, typically increasing. Now, intuitively, what is entropy? Kind of a hard thing to get some good intuition for. What is entropy?
The randomness of particle movement.
That's one way to think about it. It's how much randomness is in the system, or how much disorder is in the system.
Disorder.
Another way of thinking about it that the author didn't spend as much time emphasizing is entropy is also energy tending towards being less useful. If you think about the sun, right? What do we, being the earth or living things here on the earth, get from the sun? And the first people would think energy. We get energy from the sun, right?
Yeah.
But we get energy from the sun, but the earth also emits energy. And relative to the sun, how much energy do we emit? We emit basically exactly as much as the sun emits at us.
How?
The sun shines the energy at us and we re-emit it right back into space.
How do we re-emit it?
If we weren't re-emitting it, what would happen to the earth?
It would heat up.
It would keep heating up and heating up and heating up. And we wouldn't be able to survive on this planet. So we get energy from the sun, yes, but we also emit that exact same energy back from the sun. Think about you as an individual human being. What do you get from food?
Energy.
Energy, but you emit as much energy as you consume. Why do you need to consume the energy to begin with? You're just consuming and emitting, and it's all balancing out to zero. What are you really getting from the food?
Work.
You're able to do work as you convert energy from being low entropy energy to high entropy energy.
Oh.
More useful forms of energy to less useful forms of energy.
So
I don't know the exact ratio here, but it's something like, it's within an order of magnitude. For every 1 photon we get from the sun, we emit 20 photons back into space, we being the earth. And so the sun, what kind of photons are we getting from the sun?
UV, I don't know.
Visible light for the most part, but some UV. And the most part, what do we emit? Infrared.
Heat.
Heat, which is typically in the infrared range. And so we're getting low entropy photons from the sun and emitting high entropy photons. We're in the process of converting them from low entropy to high entropy. We somehow got some work out of them, some use out of them. And the byproduct of work is almost always and forever heat. It's very easy for me to convert work into heat. That takes no skill at all. I do that. I just did some friction on the carpet, which created heat. I moved my leg through the air, jiggling the atoms, which created heat. You take a box and you slide it on the ground, you create heat. Converting work to heat, that is extremely easy, that's extremely simple. Anyone can do it. The hard part is converting heat back to work. If I take a book and I slide it across the desk, then what happens? It eventually comes to a rest.
Yeah.
What was going on there?
Friction overcame its.
It had its initial kinetic energy, which friction ate up, and it was converted into just heat. We never see the inverse happen. We never see a book start absorbing heat from the table and start spontaneously moving and start flying back over. Why not? The energy's still there. We see the process go one way, we don't see it go the other way. How can we view this in terms of randomness increasing? Think about when you slide a book. You've got billions of atoms all with uniform velocity just moving in sync with each other. It's a crazy amount of order.
Yeah.
But as it's sliding around and jiggling things, it's now creating all sorts of random motion. And when your book's done sliding, there's all sorts of random motion that was a consequence of that uniform motion. And so that's one of the ways you can think about it, being very ordered motion being converted into very chaotic, unordered motion. So trying to give you some high-level views for how to think about entropy. We'll have a lot more to say about entropy and a lot more to say about this process of converting heat to work. Remember, work to heat, stupid easy. Heat to work,
It's hard.
that's much more difficult. Okay, so before we dive into the actual material, let's do a quick recap on the important things from last chapter. So first off, what was our first law of thermodynamics? Huh?
Yeah, have to give me a second.
It was the change in internal energy of a system is equal to the amount of heat coming into the system minus the work done by the system. It's our new conservation of energy formula. And so this internal energy accounts for all the kinetic and potential energies internally in whatever your system is that you're talking about.
So it's just calculating internal energy.
It's just internal energy.
Okay, that's right.
Okay. Typically, we were doing internal energy for an ideal gas. That's pretty much exclusively what we've been talking about for the past couple chapters. That's going to be the case pretty much for this whole chapter. Just an ideal gas. So in particular, when we had an ideal gas, so PV is equal to nRT, and when we had n as constant, we're not changing the number of molecules that we're working with. We had our equation for work. You remember that? Work is equal to the integral of your pressure times your little change in volume. If your volume's not changing, then your ideal gas isn't doing any work. What's our most dumbed down version of work? Force times displacement. If there's no displacement, there's no work. In order for a gas to do displacement, the volume has to change, expand or contract. So if there's no change in volume, there's no work.
Yeah.
Okay.
N is not molecules, is it?
N in this case is the number of moles. And we use capital M for you actually counted each of the individual molecules.
So what's a molecule versus a mole?
A molecule, that's like counting the actual individual H2O molecules. A molecule, 3 atoms together right there. How many water molecules are there in a cup of water? I have no idea. How many moles of water is it? Maybe a couple hundred.
Yeah, a couple hundred grams.
Yeah. So
N has got nothing.
N is the number of moles of the molecule. So if I have a cup of water, then I probably have a couple hundred moles. How many individual water molecules do I have? Not even close to a trillion. Way more.
More?
Yes, way more.
Yeah, okay.
Okay, so ridiculously high number. So capital N, always a ridiculously high number. Little n is a more reasonable number. It's the number of moles of that thing, rather than the number of individual molecules.
A mole is just 1 gram of hydrogen, right?
1 mole is how many hydrogen atoms you have in 1 gram of hydrogen. That's a good way to think about it. The technical definition is how many atoms of carbon-12 you have in 12 grams of carbon-12. But basically logically equivalent. Okay. And so now in the special case of our ideal gases, the internal energy, we stressed this a lot last time, is simply a function of the temperature. If the temperature goes up, internal energy went up. If temperature goes down, internal energy goes down. Internal energy is just a function of the temperature, and the way we calculate it is it's the number of moles times its heat capacity times its change in temperature. That gives you the change in your internal energy.
That heat capacity threw me off so far. I didn't realize it was a constant.
Yeah, it's just a constant depending upon what material you're talking about. High for water, low for other things, like a metal. Okay. Now, we talked about 4 particular types of processes and spent a lot of time on each one. So we talked now about an isothermal process.
Temperature's constant.
Isothermal means that the temperature is constant. Now, if the temperature is constant, that means the temperature is not changing.
There's no heat.
Not no heat.
Oh.
There's no change in internal energy.
No internal energy, that's right.
So if the internal energy is 0, then however much heat is coming into the system is how much work the system must be doing. These must perfectly cancel each other out, or in other words, work and heat must be equal to each other. So then we calculated the work, we did the actual integral, we calculated the work, and it came out to nRT times the natural log of V2 over V1, or nRT times the natural log of initial pressure over final pressure. Notice that those are reciprocals, or those, one's final over initial, this one's initial over final. 2 different ways of writing it. And the Q is just the same as the work, so you can also calculate heat the exact same way you calculate the work for isothermal. Good so far?
Yeah.
Okay. Isobaric just means that the pressure is constant. And what is the integral of this if P is a constant? You can just pull out the P and integrate dV.
Yeah, it's V2.
And so it's just V2 minus V1 multiplied by the constant. There's the work in an isobaric case. What is the heat going into the system then? Well, the heat going into the system, now imagine I move work to the other side, so then Q is equal to delta U plus W. The heat then is going to be equal to however much work you do. We got to get enough heat to account for whatever work you did, plus a change in internal energy.
Yeah, okay.
If the internal energy of the system went up, then we must have added heat in an isobaric case. Or if the system did work, we must have added heat. Or the internal energy went down to compensate. So those two equations make sense for isobaric, right?
Yep.
Isochoric means the volume is constant. If the volume is constant, how much work is my gas doing?
Nothing.
None. So the work is 0. And so now heat is just equal to the change in internal energy.
That's right.
Good?
Yeah.
And then the one that we spent the most time on was adiabatic. In an adiabatic process, then the heat coming into the system is 0. And if the heat is 0, then what is W equal to? It's equal to the negative of your change in internal energy.
Negative.
Internal energy equals negative work.
Yeah.
So work equals negative internal energy. So work equals negative the change in your internal energy, which is equal to, notice what we did there. What is your internal energy equal to? NCV T2 minus T1. If you want to flip the order of these, you can pull out a negative sign.
Oh.
So flip the order, pulling out a negative sign to make it positive. So this one is the one that will trip you up a couple times when you calculate the work done by an adiabatic process. It's the initial temperature minus the final temperature, not the final temperature minus the initial.
Interesting.
And then we derive this other way of writing it, 1 over gamma minus 1, where gamma is a property of whatever gas you're talking about.
Yeah.
1.4 if you're talking about a gas composed of 2 atoms, a diatomic gas, a 2-atom gas.
Well, doesn't that also depend on... Oh, yeah, never mind, you're right.
Yeah.
I remember.
And then doing the substitutions, we also replace T1 with the P1 over times V1, P2 times V2. So we did the substitution going from this to this, just another way to calculate it. Now what we spent the most time on with an adiabatic process was deriving these relationships between temperature and volume and pressure and volume. That's what we spent most of our time with. And so the temperature times the volume, the initial temperature times the initial volume to the gamma minus 1 is equal to the final temperature times the final volume to the gamma minus 1. Initial pressure times the initial volume to the gamma is equal to the final pressure times the final volume to the gamma. And that's the important stuff from last time, and we did derivations for all that stuff. Well, some of it being a definition, like that was... Oh no, we actually derived that from the definition of work. So yeah, pretty much derived all of it. Good so far? Okay, so now starting this book, this chapter, I initially started out talking to you about reversible processes. Now, what on earth is a reversible process?
Process is reversible.
So, give you the first intuition the author tries to give you. Imagine that I have an ice cube inside this big metal box. The ice cube is exactly 0 degrees Celsius and the metal box is exactly 0 degrees Celsius. And so now, it's almost like energy can kind of flow between the ice cube and the container however it wants. It can kind of free flow. And so it can go from being 0 degree ice, energy can leave the container, or can leave the ice cube and go into the container, making it water, still at 0 degrees, or back and forth back to ice. Now this is a lie. This does not happen. If two objects are the exact same temperature, how much heat flows between them? None. So a reversible process is a fiction. This is not real. It does not happen. It would not happen that if that were exactly 0 degrees Celsius and that were exactly 0 degrees Celsius, that heat would flow between these things. But it almost would. It's right on the verge of flowing. And so if I just added a little delta T, an infinitesimal amount of temperature to the container, then the heat would flow into the ice and melt the ice. And if I subtracted just an infinitesimal amount of temperature from the container, now the heat would flow out of the water and make it back into an ice cube. And so that is what we mean by a reversible process. We mean it's right on the verge. An infinitesimal change to the system can get it to go back and forth.
Doesn't ice expand the volume?
Doesn't ice expand the volume? Yeah. This was for an ideal gas. So it's not doing work just because it's expanding, if it's in a perfect vacuum.
Can't you create pressure based off that?
No. So perfect vacuum, out in space. There's no gravity, there's no nothing. There we are just floating around. Whatever.
So why can't we use ice to create pressure?
Forget about it's a perfect vacuum, so there's no pressure because there's no gas.
Oh, I get this.
Okay, so pressure has nothing to do with this. Just trying to give you intuition for a reversible process. It's not real, but we can get really, 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 really close. It's almost reversible. So anytime I say reversible process, you can just think to yourself an almost reversible process and you'll probably be pretty good. Now, if these things aren't real, why do we care about them so much? Well, maybe before I say a reversible process, give you an example of a non-reversible process. What's an example of a non-reversible process? You got your water, it's at room temperature, and you drop an ice cube into it, and the ice cube melts into your water. That's a non-reversible process. There's no slight tweaking I could do to make that ice cube reform inside your water and re-separate out. That's an irreversible process. And the majority of processes are irreversible processes. I slide a box across a carpet. There's no slight tweaking I can do to get the box to suddenly reverse itself and slide back.
What does slight tweaking mean? What do you
Like
tweak?
over here, if I change the temperature by an infinitesimal delta T, and I make this just slightly more than 0 degrees Celsius.
That's so...
How much more? As arbitrarily small as you want. But if it's just slightly more than 0 degrees Celsius, then heat will flow and we'll get water. And now if I make it slightly less, heat will flow and it will go back the other way. And so it can reverse itself with these slight tweaks, these infinitesimal changes.
Fiction.
Yes, this is fictional.
Okay.
It's not a truly reversible process. This does not happen in nature. If two systems are in thermal equilibrium, no heat flows. But it almost does. It's so close. Right? So, why do we like reversible processes if they have nothing to do with reality and all the processes we see are not reversible processes? Well, for one, for very gradual processes, we can approximate them as almost reversible processes, making very slight changes to system. But more importantly, these types of systems are always in thermal equilibrium. Question, what's the temperature of the system?
0 degrees Celsius.
0 degrees Celsius. I have my cup of water, I drop an ice cube in it. What's the temperature of the system?
2 different temperatures.
Yeah, what do you say? It's not really a well-defined temperature. And so when it's in thermal equilibrium, the temperature is well-defined. So that's one of the things we want is a well-defined temperature. And the other things that we don't have are drastic jumps in temperature. Temperature will always change very continuously, very gradually, and so it will make a nice continuous curve when you try and plot the temperature. So another example of a non-reversible change is lighting a stick of TNT inside some chamber. It will blow up and suddenly the temperature will suddenly change, right? Temperature will be low, and then it goes off, kind of chaotic for a second, and now the temperature's suddenly up here. And so there's a discrete change in temperature. It jumps. It's not a continuous change. So those are the two things we want. We want to talk about processes where the temperature is always defined, and we want the change in temperature to always be continuous. Why do we want these two things? Ultimately, where we're going when we calculate entropy, we're going to be calculating an integral of some temperature function. And if our temperature function isn't continuous, or it's undefined in places, you can't integrate over it.
Interesting.
So we're going to look at processes that aren't reversible processes. We're going to model them with reversible processes, and in that way we're going to be able to do our calculations. And it turns out it's going to be fine. The same way that turns out calculating a change in entropy is like calculating a change in potential energy. When I say I take this 1 kilogram calculator and I lift it 1 meter in the air, and that's the path I took, you don't care the path I took. You just care where I started and where I ended. And you can pretend the calculator took any path you want as long as you know where it started and ended. Turns out with processes where we're calculating entropy, we're not going to care exactly what the system went through to get from point A to point B. We're just going to care that it went from point A to point B, pretend that the path was a nice, continuous, reversible path, and calculate the entropy and it comes out the same.
So it's all fiction.
So it's a useful idealization for calculating a real change in entropy. Okay, so that's what we'll be doing Hopefully you stress the entropy enough. Now let's jump into a heat engine. And like I said, what's real easy? Converting work to heat. That's stupid easy. Just did it. Converting heat to work, that's the hard part. Reversing this process, reversing the transfer of work to heat to work, that's the hard process. And so now we introduce what we call a heat engine, which is exactly what it does. When you drive your car, what is your car doing? It's generating heat ultimately from the gasoline and using that to try and get some work in the process. And so it's trying to convert heat to work. That's a hard thing. So this is going to be our very high level view for heat engines in general. What do they do in general? They're fed in some amount of heat, Q sub H. The width here is meant to try to quantify how much heat is coming in. And as that heat flows from some hot source to some cold source, we try and get some work out of it in the process. So you light up your gas, it gets really hot, and in the process of it ultimately escaping your car, we get it to push a piston. So as it goes from the hot source to the cold source, we try and get some work out of it. So we already get for free in nature that energy, that heat flows from hot sources to cold sources. A heat engine tries to get some work out of the process along the way. That's a big idea of a heat engine. Make sense so far?
Yeah.
Now, what then is how do we calculate the efficiency of our heat engine?
Work divided by your heat.
Yes, exactly. What we care about is how much work we're able to get out for how much heat we have to put in. So W over Q sub H. Now, with how this is written, notice that W is the same thing as Q sub H minus Q sub C. This distance is this distance minus this distance. That's what I was trying to make very clear with my drawing there. And so I can also write this as Q sub H minus Q sub C over Q sub H. Or if you write that as two fractions, 1 minus Q sub C over Q sub H. Those are two different ways that you'll see it. But there's the idea, and there's the efficiency for some particular engine. There's how you calculate it. And we'll do that for some actual engines. But before we jump into an actual engine, this is just a high-level view for the basic idea behind all engines. Let's also look at the basic idea behind all refrigerators. What's the idea behind a refrigerator now? Because notice a refrigerator is very strange. It's trying to get energy to go from the cold source to the hot source. You've got your refrigerator, and you're kind of trying to pump heat out into the outside. And so how does it do that? And so intuitively, how does that work? If I'm going to get heat to flow from a cold source to a hot source, I'm going to have to do some work to do it. So a refrigerator does work to get cold to flow to hot. A heat engine lets hot flow to cold and produces work as it goes. Good so far? Now, I think you have good intuition for how a heat engine could work, but maybe how on earth can I use work to get cold to flow up to hot?
Pressures.
Let me give you just a stupid simple way that you could cool down this room. I give you a piston with some gas in it that you can manually expand and contract. Okay, I have you come in here and I have you expand the piston. You pull it apart. As the piston expands, what happens to the gas inside there? The temperature goes down. The pressure goes down and the temperature goes down. And so now it's going to get colder than it was. And so now it's going to be colder than the room around it. And so it's going to absorb heat from the room around it. And then I have you go outside and I have you compress it really hard. And as you compress it, then the temperature of the gas inside there shoots up. And now it's hotter than the surroundings outside, and the heat flows to the surroundings outside. And once it cools down enough, you bring it back in and you expand it again. Okay, there's a very stupid way you could try and cool down this room. But that's the basic idea. So you've probably seen those little coolers that they have like hanging inside of windows that you stick out of your window. So that's what this is meant to represent here. So how does this work? You've got some coolant, some fluid, something in there. And what happens is, it flows and it goes, that red dot right there represents a compressor. A compressor, yeah. So it compresses it really, really hard together, heating up whatever the fluid is. So as the fluid goes outside, it's now really, really hot. And so it's releasing heat outside. And then, when it comes to that part, then that is some sort of, what do they call it?
Condenser?
Not a condenser, what are they called? Now it's going to bug me. Some sort of valve, but basically past this point, it's allowed to expand again. We're not keeping it all tight together.
It's sort of that piston idea.
Sort of the piston idea. This is where we now allow it to expand again once it goes past that point. And so once it passes this point, then the fluid's able to expand again. And as it expands again, it absorbs a bunch of heat. And then, once it gets to the compressor, it gets compressed again, lets it out. The compressor needs to be plugged into your wall to actually compress. That takes work. And so that's using electrical energy to do your work to keep doing the compressing. And so that would be the work coming into the system. The Q sub C is the heat being absorbed inside, and the Q sub H is the heat being absorbed outside. The Q sub H is always way more than the Q sub C because the work itself also turns into heat.
An expansion valve.
An expansion valve, thank you. It was something simple. Yeah.
Some kind of valve.
Yeah. Okay. And so, that's how it works. Now, what if it's wintertime? What do?
You want to flip the process.
You flip it, you just turn the machine around, and you can take these machines, and in wintertime you can turn it around. And even though, in wintertime, even if it's 0 degrees Celsius outside, if it's freezing outside, there is still a lot of energy outside. That is still 273 degrees Kelvin. There's still a lot of energy out there you can pump back in. And so it just works in reverse. It sucks heat from the cold side outside and pumps it into your house, while at the same time the work it does pumps into your house. And so that is typically called a heat pump. And it's way better than just using a space heater. When you plug a space heater into your wall, that's just converting work to energy. That's doing the stupid thing of just me dragging my foot back and forth. This one, much better, because you're using the fact that there's energy outside that you can pump in while your work's also being converted to heat. And so it's a double whammy.
You still have to do the work.
You still have to do some work to get the pump in, but rather than just converting work to heat, you're doing work to pump energy to create even more heat. And so you can always get more heat in your house with something like a heat pump than you can with just like a space heater.
I see. Yeah.
Good?
That makes sense, yeah.
Okay, so talked about heat engines, talked about refrigerators from a high level. Now let's jump into an actual heat engine, what goes on inside a piston inside your car. And this is called the Otto cycle. So here's the 4 stages, A, B, C, D. Sorry, the green doesn't show up too well. And your piston goes through these 4 cycles, so let's get intuition for each of these 4 cycles. So starting at A, what happens is your piston is completely expanded. Remember, that weighs volume. So your piston is completely expanded, and at this point, it has gasoline fumes mixed in the piston. So I'll use green for when there's gasoline fumes in there. And in going from A to B, the piston is compressing.
So volume.
Down to some smaller volume. So this is some small volume. This is R times the volume, which is the expansion rate of your piston. For most cars, I think it's about 8. Might be 10.
Expansion.
So yeah, when the piston is fully expanded, it has 10 times more space than when it's fully contracted.
Oh, it's just ratio.
It's just a ratio, the expansion rate. So going from A to B, what's happening is the piston is just really compressing that gas.
Yeah.
So that's going from A to B. Now the gas is all nice and compressed. Now, at the top of your piston, you have something called a spark plug. And it ignites. And when it ignites, what happens?
The fumes.
Yeah, the gasoline fumes ignite, and they burn really quick.
First.
And so suddenly, the energy in that shoots up very high. And so going from B to C, that's a very fast change. It lights up. And that's when your heat now is entering the system. That's our Q sub H coming into the system, our Q sub H.
Yeah.
So there it is, and now you get what is called the power stroke coming back down. So that gas now is pushing very hard, much higher pressure pushing it down than the pressure when it was going up. Shoots down very hard. I'm using blue there to represent the fact that we burned up the gasoline fumes. No more gasoline fumes. As we go from here to here, they've been burned. That's going from C to D, that's when you get most of your work out of the system.
And so it's going to give you way more work than the work you have to push down.
Right. This work, as it shoots down, is much higher than the work you had to do in pushing it up.
Higher pressure. That's why. Okay, yeah.
Yep. Okay, and now, once it fully expands again, so you get your power stroke, you get the work out of it, and it fully expands again, then the piston does a full cycle going back up and down. So it goes back up, so it comes down here, now it's going back up. It opens a valve at the top right to let all the cold air flow out, and then as it opens back down, that valve closes and this one opens, sucking in fuel with gas fumes.
Is this all electrically done? How is all this done?
No, that can be done in a very mechanical way. You can have it rigged up so that every second time this hole's open and every third time this hole's open or whatever.
That's pretty complicated.
But anyways, that's basically how it works. And so this air that it pushes out, the heat that that air leaves with is your Q sub C.
Exhaust.
Your exhaust. But your exhaust,
It's not cold.
there's still a lot of energy in that exhaust that you're just letting go into the atmosphere.
Fumes, you're saying?
Yeah, in your fumes. They still have a bunch of heat in that gas.
So why is it QC? It would be hot.
QC because that's for the energy leaving the system. You're not capturing that energy. So QC does not necessarily mean it feels cold, and QH does not necessarily mean it feels hot. It's just that our heat flows from our hot source to our cold source. Maybe should have said our hotter source to our colder source. This could be flowing from negative 100 degrees Celsius to negative 101 degrees Celsius.
Nice.
Okay, good clarification.
But you're saying there's still fumes left, and so not all.
Not necessarily still gasoline fumes left, but it's just you put a lot of energy into heating up that gas, and so that gas has a bunch of internal energy. And you're just releasing it out to the atmosphere. And there it goes.
Because not all of it goes to pressure pushing.
Yeah, that gas did not lose all of its internal energy doing this expansion. And so some of the energy you dumped into it, it just flows out and away it goes.
Why don't we just make bigger engines, bigger pistons?
Well, so now let's do some of exactly what you're talking about doing. First off, let's get comfortable calculating the work and the heat in each part of this cycle just to make sure you understand the cycle. Okay, so going from A to B, what kind of process is that? No, it's going to be one of these four processes right here. Isothermal, isobaric, isochoric, adiabatic.
It's going to be a constant temperature.
No,
Because your temperature.
temperature is definitely changing as it compresses. Temperature is going up.
Yeah. There's no heat transfer.
There's no heat transfer going from A to B, so it's an adiabatic process. So what is the work done here? It's N times CV
Minus negative work.
times the temperature at the start minus the temperature at the end.
T1.
So the temperature at A minus the temperature at B. Backwards from what you want it to be. What's the heat in going from A to B?
A would be the heat. QH minus QC.
It's just zero. It's an adiabatic process. In this part, there is no heat being added to or coming out of the system. There's only heat coming in from B to C and heat leaving from D to A.
Yeah.
From A to B is adiabatic. There is no heat. Good? At the part where you are compressing the piston, you are not adding heat to the system and you're not taking heat out of the system.
It's the same. You're just compressing it.
You're just compressing it. So it's an adiabatic process.
Okay.
Okay, now going from B to C, what kind of process is that?
No volume. No pressure.
No, you had it right before.
Volume.
The volume at the start and the end are the same.
Yeah.
So it's an isochoric. So our heat is just our change in internal energy. So here, our work is zero, because the volume doesn't change. And what is our heat? We're talking about isochoric right here. It's just our change in internal energy. So it's N times CV times which temperature minus which temperature?
B, C to B.
Temperature C minus the temperature at B. Good. TC minus TB. All right. Now going from C to D, what kind of process is that?
Temperature's the same.
Not temperature is the same.
The temperature's not the same. It's the same adiabatic.
It's adiabatic. There's no heat. That's which one it is. So once again, we get an adiabatic process. So our heat is going to be 0, and our work, what is our work going to be? It's going to be N times CV times, which temperature do I write first?
DC.
C. Remember, backwards from what you want it to be. TC minus TD. Okay, and then finally going from D to A, once again, that is a isochoric, right?
Yes.
So that is going to be N times CV times, what's our temperature on this one?
The same. No. How do you say that? It's A.
The temperature at D minus the temperature at A, right?
Yes.
It's backwards from what you want it to be. Initial minus final rather than final minus initial. Okay, now what is Q sub H? Q sub H is our heat coming into the system from B to C. So our Q sub H is this number. Do I have my red marker? I guess I'll just do it in blue, sorry. Q sub H is right here, and then this is our Q sub C. Right? Except for this is the heat coming into the system. We're thinking about Q sub C as the heat leaving the system, so it's actually the negative of that. So Q sub C is going to be the negative of this thing. So this is negative Q sub C. Because this is how much heat's leaving the system, but we think about Q sub C as how much heat, or sorry, this is how much heat's coming into the system. We think about Q sub C as how much heat is leaving the system. Okay, so there we go. There's our Q sub H, and there's the negative of our Q sub C. So let's calculate the efficiency now of the sink. Efficiency, how do we calculate the efficiency of a heat engine? This is how it is for all heat engines. It is just QH minus QC over QH.
Yeah.
What is QH? It's this term. What is QC? It's this term. Now notice that when I do QH minus QC, that's this minus this, I can take that value and factor it out. And when I divide it by Q sub H, it's also going to have an NCV. In other words, all the NCVs are going to cancel out. Now we're going to be left with is the temperatures.
Okay.
With me so far?
Yep.
So make sure we understand the signs on everything here. TC minus TB is right here. Now notice that this is a negative of that. This was negative QH.
Yeah.
Right? And we had a minus QC there.
But then your plus would have to be in minus, wouldn't it? Because you're flipping it.
So
That plus
flipping this out pulls out a negative sign.
Okay. Oh, and then
Cancel out the negative signs, gives you QC. And then we're doing minus QC.
Yeah. Okay. That makes sense.
Okay. Now, did I say all that right? I think I did. Okay. What I have here is written correctly. I might have said something weird. I'm not sure if I said something weird. But this is our equation. Okay. Now, what do I know about adiabatic processes? Remember, I have these relationships right here.
There's no heat transfer.
For adiabatic
You're
processes,
saying
then this relates temperatures to volumes and pressures to volumes. So I'm going to be using that fact. So we have two adiabatic processes here, from C to D and from A to B. And so I know that the temperature at A times the volume at A, remember that the volume at A is R times V. So our temperature at A times our volume at A to the gamma minus 1 is equal to our temperature at B times the volume at B to the gamma minus 1. So this is just using this relationship for the adiabatic process from A to B, just stating it. Now, I'm going to divide both sides by V to the gamma minus 1, which gives me this.
Okay.
Okay, and our other adiabatic process is going from C to D. So the temperature at D times the volume at D to the gamma minus 1 is equal to the temperature at C times the volume at C to the gamma minus 1. Divide both sides by the volume to the gamma minus 1 gives you this.
Yeah.
So I can rewrite TB in terms of TA, and I can rewrite TC in terms of TD. So rather than having TA, TB, TC, and TD, I'm going to replace my B's and C's with A's and D's, so then I'll only have two variables, TA and TD. So that's all I'm going to do. Going from here to here, I am going to replace, anytime you see a TC, I'm going to replace it with a TD to the times R to the gamma minus 1. Anytime you see TB, I'm going to replace it with a TA times R to the gamma minus 1. So going from here to here, that's that. The TA is still just TA, and the TD is still just TD. And now in the denominator, TC becomes TD times r to the gamma minus 1, and TB becomes TA times r to the gamma minus 1. Now going from here to here, I'm just going to factor TD minus TA out of the top and bottom. So redistribute to make sure you can see how this works. TD times r to the gamma minus 1 gives me this term. Negative TA times r to the gamma minus 1 gives me this term. TD times negative 1 gives me negative TD. Negative TA times minus 1 gives me TA. And then for the bottom, it's easier to see. I think it's obvious. Good? Okay, now you can cancel that out, top and bottom. Ba-doop, ba-doop. And you get r to the gamma minus 1 minus 1 all over r to the gamma minus 1. Or break up into two fractions, this over this minus this over this.
And gamma is just constant.
And the gamma is a constant depending upon your gas.
Okay.
If your gas is diatomic, it's 1.4.
It's okay, it's that one.
Yep, the property, that one's dictated by your gas. And so that is how you can calculate the efficiency
Shape.
of the Otto cycle.
Okay.
Now notice, what is this saying? If you want a really good efficiency, what should you do?
Massive pistons.
Massive pistons, really big R's. So why on earth do we just use these little dinky pistons? Why don't we make them absolutely massive?
Not very.
And as you make the piston more massive, then in your compression stroke, so larger piston means I'm going to compress the gas even more as I compress it. And as the gas becomes more and more compressed, what happens?
Temperature increases.
Temperature shoots up. And the problem that you have is,
Melts the metal.
as this is going up, you might get halfway done, and the fuel will get so hot, it will just self-ignite.
Oh, how does that work?
Just once you get something hot enough, it's going to ignite. It's going to, basically, igniting is it starts breaking chemical chains. And so the chemicals are stuck together, but if they get hot enough, they'll jiggle apart and break apart. And it'll start a chemical reaction of fire, burning.
So just having something heat up enough will light on fire.
Yeah, you've seen this all the time in movies, like a guy, a stick caveman, and he's got his piece of wood, and he's rubbing it back and forth, spinning it, trying to get that wood to get a high enough temperature that it ignites.
That's so strange.
Gasoline's the same way. So, you get it spontaneously combusting.
Well, can't you do like some different kind of gasoline?
Yeah, so this is exactly what, at the gas station, when you go and you see the different types of gasoline, you see regular versus premium. A more premium gas is one that can withstand a higher temperature without igniting.
That's so cool.
So it won't ignite. So if you've got more of a sports car, you've got bigger pistons, then you need the more expensive gasoline to make sure that you don't have this issue.
Why would you put premium in a normal engine?
Why? I wouldn't.
Does it matter?
Not that I'm aware of.
Well,
Not
if it's
if you go
harder,
up.
what if it doesn't combust when it gets very hot?
Oh, the gasoline you can get to combust. That's not a problem.
Okay.
So that's a real easy part of this process. The hard part is getting it to not combust too soon. And it was a problem with kickbacks in your cars, clunking in the cars that people would hear, with their pistons firing when they shouldn't be firing. And so it's trying to go up and it fires and goes down, and you're not able to get near as much work out of it. Right? It's compressing. If it just ignites right there, it goes down, and it can also lead to mechanical issues, actually ruining your engine. So, not a good thing. So how annoying is it that we can't do that?
Well, we still can. Why don't we just do massive engines and then different kind of
Well, you can only do so much to the gasoline. You still have something that's going to ignite. And so the plan that they said is, I want a really efficient engine, and I want to get around this problem. And so they came up with the idea of a diesel engine. And how does a diesel engine work? The diesel engine, you don't put the gas fumes in until the piston is all the way expanded. So it comes up here, the piston is all the way expanded, or all the way compressed, I mean.
Yeah.
And then you have an injector now that shoots the gas fumes in there while it's completely compressed. And it spontaneously ignites. There's no spark plug in a diesel engine. And so it's completely compressed, and then you shoot the gasoline in there as this piston is opening now, so it kind of has an exploding opening as the heat comes in, and then you get the rest of the power stroke. And so diesel engines are much more efficient than car engines. But an engine that functions this way is much more elaborate and complicated than an engine that works this way. So you can pay a lot more for your engine, but get a much more efficient engine, or you can pay less for your engine and get a less efficient engine.
So diesels have like better miles per gallon.
So diesels have much more engine efficiency. Typically they're carrying much bigger loads.
Oh.
And so when you start talking now about miles per gallon, it takes into account that thing. But miles per gallon per kilogram, yes. They're much more efficient.
They can't be that much harder to design to make.
It is much easier to just have the gas in there and light it up. It's much easier to put the gas in when it's completely expanded and there's no worry about managing a mini explosion than trying to inject gas into like a controlled explosion. To my intuition, this seems much, much harder than that seems. Maybe it's not much, much harder, but it seems like if it wasn't much, much harder, then regular cars would just work this way and be way more efficient. So I'm guessing it's much, much harder. And what specifically about diesel fuel that makes it function right for these things, I'm not sure.
Chemical compound.
I'm not sure if it's meant to withstand more, or if it's meant to be easier to ignite, or what. No idea. I still would not put diesel fuel inside your car though.
That's right.
Okay, so there we go. Those are our heat engines, giving you two different examples of heat engines, doing some calculations for if you had to calculate the work or heat for any part of the system. Okay. Any questions before we now jump to the second law of thermodynamics now?
That was this, oh. That's all the first law.
No, this was just heat
This is the
engines.
second.
A little bit with refrigerators and heat engines, just helping you understand what these things are. Okay, so now our second law of thermodynamics. Here's a couple ways that you could state it. I've already stated it for you a few ways. But here's one of the ways to state it. It is impossible to get a 100% efficient heat engine where it converts all the heat going into it directly into work and no heat goes to the cold source. Impossible. Doesn't exist. Can't do it. You can't have a perfect 100% efficient engine. That's one way to state it. The logically equivalent way to state it is you can't have a free refrigerator. You can't have a refrigerator that doesn't require any work. And these two are logically equivalent versions of each other because if you can give me this, I can make one of these, and if you give me this, I can make one of these. And the book had a little diagram to quickly show you how to do that. I didn't want to draw out the diagram, but easy to see. So, two equivalent ways of stating the second law of thermodynamics. Impossible picture or impossible picture. Okay. But, theoretically, what is the most efficient engine we could have?
The Carnot.
Now remember, work to heat, stupid easy. Reversing that process, heat to work, much harder. And so, our hypothetical Carnot engine here, to try and make it as efficient as possible, we are only going to use reversible processes. Ones where we can easily recapture the heat we put in, take it right back out. So, we're going to talk about the Carnot cycle. This is a completely fictional engine. How might we build this engine? Here's what I'm going to do. I'm going to have one absolutely massive block of just steel or something at our temperature Tc, our cool temperature. And I'm going to have another massive block of steel at our temperature Th, our hot temperature. And I'm going to have some piston. And here's what I'm going to do. When that piston is right here, I am going to bring it into contact with my cooled big metal block. Right? So I got my piston there. I'm going to hold my cool metal block at the bottom of it. And since they are almost reversible, even though they're the exact same temperature, because this is the Tc temperature, my cold block is infinitesimally hotter. And so heat flows out of my cold block into the piston, giving it energy. And so that piston is gradually getting energy, and it's expanding, it's expanding, it's expanding, it's expanding. You with me?
Yeah.
And once I've given it just enough energy that it can finish its expansion, I'm going to pull my heat block away. So right here at D, I pulled my cold block away. And I'm not putting energy into it anymore. And it's going to keep expanding, expanding, expanding until it just stops. Whew. Perfect. And now, what am I going to do? I'm going to put my heat block now on it. Which is, oh, I said this one backwards. Our cold block, we were absorbing energy to get it to compress.
So you need your hot one.
Yeah, so we were sucking the heat out of it very slowly to get to compress, 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 compress. At this point, when we knew it was going to get all the way and compress, we pulled it apart and it finished the process. And now we got to get it to expand again. So now right here, I put the heat block underneath it, and it starts absorbing heat from that ever so gradually, because the heat block is almost the exact same temperature as the compressed gas. And it slowly, slowly, slowly expands, and once I know that it's got enough heat to finish its expansion, I pull my block away, and it finishes the expansion. And very gradually, I can get this piston to go up and down in this way, in a very reversible way, being very efficient with our energy. And that's what this Carnot cycle is representing.
Why does it finish it?
Huh?
Why does it finish it?
Why does it finish it?
Like when you remove the block. Why does it finish expanding or contracting?
Because there's still energy left.
So the temperature is now going to drop
Yeah.
as it finishes the expansion.
Yeah.
But it just finishes the expansion, there it goes, and so the temperature is going to drop.
Well, when you remove the block.
When I remove the block. So here I'm adding heat. This point, I've added enough heat that as it finishes the expansion, the temperature is going to end exactly at Tc. So I'm no longer adding heat, this is an adiabatic process. So isothermal, adiabatic. Isothermal, adiabatic.
Okay.
And all the times where we're adding or removing heat, we're doing it with the heat source, basically at the exact same temperature as it. So it's a completely reversible process and completely, basically in thermal equilibrium with the hot source or the cold source that we're coming from. All right? You would never use this in a car. It's a ridiculously tedious, slow cycle, just very gradual changes as we go, but very efficient. Okay, so here's as efficient as we could possibly be, only using reversible processes, trying to hang on to all that energy. And the work done, obviously, is the area right there. Don't need to color that in. I probably didn't stress that enough right here. Work, here's work done by a system, work contracting system. The difference is the area. Okay. Anyways, so we're going to calculate the efficiency of the sink. Now, if I'm going to calculate the efficiency of the sink, what's efficiency?
Your QH minus
QH minus QC over QH. Okay, so what is QH then? That is the work done in going from A to B. The work in going from A to B has to be the same as the heat coming into the system, because it's isothermal. My delta U doesn't change, and so however how much work is being done, that's how much heat must be going in, and they have to perfectly cancel each other out for my change in internal energy to be zero, for my temperature to not change.
Yeah.
So this is our isothermal process. The work from A, or the heat from A to B is the same as the work, or you can just also see when we explained over here. Work, heat, same thing. And here it is. NR times the temperature that we're at, in this case it's T sub H, times the natural log of our ending volume over our initial volume. That's how much heat came into our Carnot engine. How much heat flowed out of the engine? Well, remember that our Q is how much heat's flowing in, so QC is the negative of how much work we did. So the negative of how much work we did, which is negative RT of the cold source, that's the temperature we're at, our cold temperature, times the natural log of our ending volume divided by our starting volume, VD over VC. If I want to bring that negative inside, then it just flips the reciprocal of our log. Remember that the log of a quotient is the difference of the logs. This is the same thing as the natural log of VD minus the natural log of VC.
Yeah.
And so, if I flip the order of that difference, that's also flipping the quotient on a log. Does that make sense? Mm-hmm. Okay, so now, I'm trying to calculate the efficiency, right? So next thing I'm going to calculate is my QC over QH. Because another way that I could write this is 1 minus QC over QH. So let's calculate QC over QH. QC over QH is, here's QC, here's QH. What do you notice about those?
The cancel.
Whole lot of canceling, at least right here.
Yep.
Those cancel, and those cancel.
And RT.
What about these inner things? So once again, notice that from D to A and from B to C are adiabatic processes, which gives us these relationships. So, my temperature at B, what's my temperature at B? TH. My temperature at B times my volume at B to the gamma minus 1 is equal to my temperature at C times my volume at C to the gamma minus 1.
Yeah.
Similarly, my temperature at A times my volume at A to the gamma minus 1 is equal to my temperature at D times my volume at D to the gamma minus 1.
Yeah.
Okay, so now I'm going to do this equation divided by this equation.
All right.
So this divided by that, and this divided by that. So TH times VB to the gamma minus 1 divided by TH times VA to the gamma minus 1 is just going to be the VB over the VA. In other words, when I divide this by this, TH's go out. When I divide this by this, TC's go out, and I'm left with this. Good? Right? Raise both sides to the gamma minus 1 power. And VB over VA is the same thing as VC over VD. So the natural log of VC over VD is the same thing as the natural log of VB over VA. So the whole point of all that is our final canceling out that over that. And so with a Carnot engine, QC over QH is the same thing as TC over TH. And so the efficiency can just be calculated as 1 minus TC over TH.
Perfect.
Good so far? Now, how do we get a perfect Carnot engine?
That is.
You make it.
No, notice that this is the efficiency. The efficiency is not 1, even though all our processes are reversible here. Why is the efficiency not 1? Intuitively, why is the efficiency not 1?
Because there's.
It's because of the work we have to do in recompressing the engine. So as we're recompressing the gas, that still takes some work. And the gas still has some pressure. If the gas had no pressure at all, then we could compress it for free. And at what temperature does the gas have no pressure?
0 Kelvin.
Absolute 0. So notice what happens if you plug in absolute 0 there. Now what's your efficiency?
1.
1.
100%.
And so you can't get a 100% efficient Carnot engine. You just need absolute 0 as your heat sink.
Which makes sense.
And intuitively, what that's doing is at absolute 0, then the pressure is 0. And so this is actually how Kelvin, when he was first coming up with absolute 0, and the idea of absolute 0 was thinking about, he was thinking about in terms of a Carnot cycle.
Oh, really?
Where absolute 0 would be where your piston was so expanded that the pressure would be 0. And so the actual definition is, he defined in the Carnot engine, TC over TH is QC over QH, and that's how he wanted to define the Kelvin scale. So that this is what would hold.
Yeah.
And then he calibrated it to make it line up with Celsius by making the triple point of water the same, basically forcing it to line up.
Oh,
To get your increments the same. But that's how the absolute 0 came into it. And so it comes from this picture. It didn't actually come from him just like we said before. But close to the same idea. So that's how you can create a perfectly efficient engine is, you gotta use absolute 0. And then you can get it.
Oh.
For ours, over here, it's to have an infinitely large piston.
Yeah.
Okay. Anyways, now, since all of these are reversible processes, then we can run this process in the exact reverse, and I can flip it around. So maybe start from A this time. Well, I don't know, maybe what's the most natural way to think about starting from this? Maybe start from B. So we got our piston halfway expanded.
So work to heat is what you're saying?
Well, going around this way now is creating a refrigerator.
What?
So if I reverse this process now Q sub C is where I'm going to be absorbing heat. And up here, I'm going to have Q sub H going out if I reverse my process.
Yeah.
Because now our work on the system is going to be negative. Here's positive work done by the system, here's negative work done by the system. Positive, negative, and so it's going to be a total of negative work done on the system.
Yeah.
So, intuitively, how do you think about that one? So, we start our piston halfway here, and we're going this way. So what's happening right here? If we're going this way from B to A,
you're putting your hot block.
yeah, we're compressing, and what I do is my hot block is infinitesimally cooler than the piston. So heat is flowing into my hot block. Because my hot block is just an infinitesimal less than the heat of the actual gas. So I have heat flowing into my hot block until it's completely compressed. And then it starts expanding, and as it's expanding, the temperature is lowering down. And there comes a point where then I get my cold block, and now my cold block is just slightly hotter than the gas. And so now it starts absorbing heat from my cold block.
Yeah.
And then the compression happens, and once it gets as hot as my hot block, I start absorbing out the heat. And then our compression coming here, and once it gets as cold as my cold block, not compression, expansion here, and once it gets as cold as my cold block, I start inserting heat. And so running it backwards gives you your ideal refrigerator. And so what now is the efficiency? Oh, we skipped that altogether with the refrigerator. Sorry. So it's not called efficiency. You can't remember exactly what they call it. But with a refrigerator, what do we care about?
Cold air coming in.
We care about how much cold air we can get to be absorbed per what? Per unit of work that we have to do. That's the ratio we care about, right? And W is the same thing as what? QH minus QC.
Yeah.
So this is also equal to QC
Nice.
over QH minus QC.
So you just lift.
So now, for some refrigerator, there's how you do it. For our special case now, where it's the Carnot cycle, because it has those adiabatic processes, those relationships, since Q sub C over Q sub H equal to TC over TH, then substituting in to that one, the equation becomes, if you want to see it completely written out, here's K, our efficiency of our refrigerator. Divide everything by Q sub H. Now you can replace all your Q sub C's with QC over QH as TC over TH, and then cancel out your TH's, and it turns into that. Now don't get confused. What's the highest the efficiency of an engine can be? What's the largest it can possibly be? The biggest number. 1, which is 100% efficiency.
It can't be that though.
What's the theoretical limit on it, right?
What's
The theoretical limit on E was 1, where we're using a Carnot engine and we're using absolute zero as our heat sink.
So why? What's
the
practical
units for
limit?
efficiency? Just percent or?
It's a ratio.
Okay.
So it's going to be, it's not going to have a unit. It's just going to be a percentage, yeah.
What's our practical limit? Like, what's the best?
So when you're talking about a car that you're driving down the road, I think that its efficiency, taking into account, if you just did theoretical limit on its efficiency, then it's going to be somewhere around 50%, I think. But in practice, you lose, I think, about 2/5 of that to just friction and stuff. So your actual car engine's efficiency is going to be closer to 30%.
That's quite buns.
Anyways, something I want to stress. The biggest E can possibly be here
One.
is 1. What's the biggest K can possibly be?
Zero?
Infinite.
What?
Infinite. It can get arbitrarily large. So don't get confused by those two numbers. I call this the efficiency of a refrigerator. That's not what it's actually called. It's just capturing the quantity that we care about, and this quantity is different from this quantity. So this quantity can be at most 1. This quantity can be at most infinite.
Okay.
Don't get confused by those. Okay, anyways, we did that, we did this, we talked about Kelvin. Okay, last thing we need to talk about is, how do I know that I cannot beat the Carnot cycle?
Because it's 100%.
It's not 100% efficient. Here's its efficiency. It's only 100% efficient at absolute zero. But how do I know that I couldn't get just infinitesimally more than what my Carnot engine spits out?
Because it's the best.
Well, how do we know that? So I'm going to really quick prove to you that it's the best with a quick diagram.
Okay.
So on the left-hand side, I have a Carnot engine. On the right-hand side, I have a Carnot refrigerator.
Interesting.
And if I were to plug my engine into my refrigerator, then we got a whole lot of nothing happening. Just moving from a hot source to a cold source to a hot source to a cold source.
Alright.
Yeah.
With me so far? Okay, now let's say that I could produce an engine that was just barely better than the Carnot engine. So what does that mean? That means that with a slightly bit more dq bit of energy here, I can get W plus dW to come out of here. Just barely more to come out. So I took just a teeny bit more heat and got to make just a teeny bit more work than what it was already doing.
Okay.
Then when I connect it with my Carnot engine here, ultimately what's happening? I have Q sub H plus dQ flowing out, but Q sub H flowing in. So in general, how much heat is flowing out of this?
Same as what's coming in.
Well, dQ more flows out than in.
What?
So out of my hot source,
It's the same.
no, flowing out here, I have Q sub H plus dQ, plus an infinitesimally more. Flowing back in, I just have Q sub H.
Well, where does your dq go?
Into doing just infinitesimally more work.
Okay.
So I get to do just a tiny bit more work with just a tiny bit more heat. You with me?
Mm-hmm.
And so in general, out of my hot source, what do we have coming out total? In total, we have dQ flowing out. Right?
Yeah.
And from our cold source, this work is going back into the refrigerator to pump back over here. So when it's all said and done, how much work am I left with?
W.
dW. And so I get dQ going into dW out with nothing going into my cold source when it's all said and done. Which, according to one of our laws of thermodynamics, is
Impossible.
impossible. You can't have it. So it violates the second law of thermodynamics to get anything more efficient than our Carnot cycle. So you can't. Otherwise, that slightly more efficient thing, I hook up with a Carnot refrigerator,
Infinite.
and I end up getting heat converted directly to work.
Perfect. Yeah.
So there it is there. Okay, let's do some example problems before we move on to entropy. Okay, example 1. In one cycle, meaning in our car engine over here, so your piston firing a bunch of times. One cycle of the piston going through all the way. One cycle all the way back to where we started.
Okay.
In one cycle, our total gasoline, or our total heat that we put in the system by igniting the fumes, is 10,000 joules. The net work we get out of it, so we get work out from this stroke, but then work goes in for this stroke. So this is our total work that comes out is 2,000 joules.
So that's your CD.
So this is the total work done. So this is, from a high level picture, we know our Q sub H is 10,000 and our W is 2,000. Okay. And then it gives us as part of the problem that we'll need for gasoline, the heat of combustion is 5 times 10 to the 4 joules per Kelvin. Wait. It doesn't make sense. It should be joules per gram. We can really quick open up the example problem 1 and make sure that I'm not saying anything stupid. And then the last thing that we're told is that there are 25 cycles in 1 second. So this piston is going through this entire cycle 25 times in a single second.
Is that accurate, like how it normally is?
I'm guessing that they got numbers close to accurate for the problem. I'm just literally writing down what the problem says. So, on example 1,
yeah, 10 to the 4 joules per gram.
okay, so not kilogram. Alright, yeah, don't know why I put the K there. Anyways, so part A wants us to calculate the efficiency then of our engine.
80%? 20% efficiency. 80.
Yeah, it's just work over Q sub H. Work over Q sub H, you can see right out the door, 20% efficiency. Okay.
8,000 QC.
Now, QC, 8,000 joules is what's leaving.
And your power is what? What was the
P now is power. What is power?
watts?
It's work over time. It's how much work are we doing per second?
What was watts?
Watts is joules per second.
Oh,
But in general, work is power over time.
okay.
So we're doing 2,000 joules of work in 1 cycle, but how many cycles do we have every second?
25.
So how much work are we doing in 1 second?
I don't know.
25 times 2,000.
What?
25 times 2,000 2,000 in a cycle, 25 cycles per second. 25 times 2,000.
450 something. 50,000.
What is going on? You're doing 25 times 2 and adding 3 zeros. Right? Make sure that I'm not saying something weird.
Yeah, you did it right.
Okay. All right, and then it also wanted it in terms of horsepower. So there's 746 watts in to make 1 horsepower. So 50, 1, 2, 3 divided by 746 gives us 67.
You wait,
You were thinking 70.
50,000 divided by 746?
So 67 horsepower roughly. Just that divided by 746.
But
There's 746 watts in 1 horsepower. This was just a conversion I scribbled up here so I didn't have to look it
Yeah,
up.
but power is not watts, is it?
Power is watts. Watts is joules per second.
Okay.
Power in general is what? Power in general is work over time.
Joules is your work, you're saying?
Joules is your work. Seconds is your time.
Okay, that makes so much more sense.
What's your power? It's how much work you're doing per second.
And work is measured in joules.
And work's measured in joules. Okay. Now the next thing they want us to calculate is how much mass is burned in a second. Now I know that 1 gram
Oh, this is in the book.
gives me off, how much is that? One of the things you guys messed up the most on your test was just looking at scientific notation correctly. What's that number?
50,000.
50,000. So this is
zeros.
50,000. That's how many joules per gram you get. In 1 cycle, how many grams are we burning in a cycle? 10,000. So 50,000 in 1 gram. We're only burning 10,000 per cycle. So how many grams do we burn in a cycle?
You're burning 10,000 watts.
0.2 grams. So every cycle we burn 0.2 grams of fuel.
But there's 25 cycles a second, so
Oh, I think I was also
5
supposed to
grams
do
per second?
per cycle. So 1 gram gives us 50,000 joules input. We only have 10,000 joules input. So we only have 1/5 of that, so we're only burning 1/5 of a gram every cycle.
What is your LC?
LC is how much heat I get in joules by burning 1 gram of gasoline. If I take 1 gram of gasoline and I ignite it, it burns. How much energy does that release? How much heat? 50,000 joules.
Over.
In 1 cycle, we're only getting 10,000 joules. So we're not burning a full gram every cycle, otherwise we'd be getting 50,000 joules in a cycle. We're only getting 10,000 joules, so we're only burning 1/5 of a gram of fuel. So when the piston expands, the gas cubes going in there, if you were to weigh them all, it's only 1/5 a gram worth of gas fumes inside the piston.
Okay, for 0.2.
So 0.2 grams. Now, that is in 1 cycle. If it's per second, and we have 25 cycles per second, what's 0.2 times 25? Just 5, right?
Yeah, 5.
300.
And then, we have 5 grams per second. How many in an hour? Now you jumped and you said, let's just go ahead and write it per minute. So if we multiply that by 60, what do we get? 300 grams, which is also equal to 0.3 kilograms if we want to make our jump to kilograms now. And now multiply that by 60 to get to our hour, which gives me 18 kilograms, right? Get your zero, because you're multiplying by 60, not by 6. So if you're driving this car along, you're going to get through 18 kilograms of fuel in an hour.
What's that in gallons?
I have no idea. I mean, if it's close to water, then 1 liter of water is 1 kilogram. Am I thinking about that right?
Yeah, that's right.
So 18 liters. How many liters are in a gallon?
4?
Is it close to 4? So probably close to 4 gallons of gas, 4.5 gallons of gas.
In 1
Probably
hour.
in that ballpark. 1 hour, yeah, driving along.
How many miles an hour is that?
There's no way for us to know that.
Well, okay.
Different engines have different efficiencies. But there we go. We just know how fast it's burnt through the gas. Okay, next example. So looking at the Carnot engine, we know that our Q sub H is 2,000 joules. The temperature of our hot block that we use to expand our piston is 500 Kelvin. And the temperature of our cool block that we use to compress our piston is 300 Kelvin.
Why do we care about Carnot cycles?
We care about the Carnot cycle because it is our theoretical max for what you could possibly get a heat engine to do.
Oh, so
Or
just getting scale
for a refrigerator. And so if you're going to do some math, you want to test it in some ideal conditions. The same reason why do we use ideal gases?
So
They don't really exist, but they're just good approximations for some things. Okay, so Carnot engine, Q sub H, 2,000 joules. There's our hot source, there's our cold source. First we need to find W. So what's W equal to in our Carnot engine?
it's a multi-process system. So there's not one way. Oh yeah, there is. That's it.
I don't know how to do that without finding Q sub C
QH.
first.
QH minus.
There's probably a good way to, yeah, that's what I'm saying. I can't see a way to do it without getting Q sub C first. Maybe he asked us to find a different order and I messed up. Let's find Q sub C first. That's the easiest one to find. What's Q sub C? Remember, for our Carnot engine, we have this relationship. Q sub C over Q sub H has to be equal to TC over TH.
QH times TC over TH.
Right, and so what's that going to be?
Oh.
Look at
2,000 times.
This is 3/5 of that, right? So this has to be 3/5 of that.
What?
You can't just see 1,400 joules.
What?
The ratio of this to this is the same as the ratio of this to this.
What to what? 2,000 from.
Q sub C over Q sub H has to be equal to T sub C over T sub H.
Oh.
What's this over this? 3/5.
3/5 of 2,000.
So this over this has to be 3/5.
How did you get 1,400? 5 times 2 is. What?
Because I was doing 400s in my head. 1/5 is 400, so. Oh my, wow.
You're confusing me so much.
Yeah, it's a 12. Sheesh.
But you're not timesing anything by 6.
Okay, the way that you calculated it also works.
I got 1,000 no.
What's 1,000 over 2,000? 1/2. What's 300 over 500?
Oh.
3/5. That's not the same. What's 12 over 20 if you want to think about it that way?
Yeah, that's how I did it.
12 over 20, take the 4 out of both of them. Gives you 3 over 5. Or just calculate the way you said it. The way you said it before, perfectly valid.
I got
You
it
say
wrong.
TC divided by TH times QH.
Oh, yeah.
That works fine. There you go. Can't believe I kept writing 1,400. Okay. Now we can calculate the work, and now the work is obviously
Your QC minus your Q, or your QH minus your QC all over your QH.
now for just work, it's 800.
Okay, what?
Because your work plus your QC has to be your QH.
You're dividing.
The heat coming in
Oh,
has to be equal to the amount of work you do plus the heat going out.
Yeah.
The energy is conserved.
QH minus QC.
Minus?
Here, look at your heat engine. You see how some of it goes.
Q sub H comes in.
Minus, oh, okay.
So
Okay.
your work-
Okay. And then finally, now our efficiency, which you want to calculate. What's our efficiency equal to?
1 minus.
You could just do the QC over W, or not, sorry, that's wrong. The W over QH if you want.
It's one-
So, 8 over 2,000.
300 divided by.
8 over 20 is probably the easiest way to
500.
think about it if you want to think about it that way. It's not 500. It's going to be a
300
percent.
divided by 500 minus 1.
20%? No, 40%.
40%. I'm not sure what you were saying, but you said probably comes up to 40%. But it definitely has to be a percentage between 0 and 1, otherwise you've messed up for sure.
Well,
So
it's
it's
1 minus TC over TH, right?
Engine that generates.
Yeah, you could have done it that way.
That's the
So,
only way to do it.
TC over TH is 3/5. 1 minus 3/5 is 2/5. 2/5 is 40%. Now, the other way you could do it is work over heat. And 8 over 20 is the same thing as 2/5. It doesn't matter. Okay, there we go. Bunch of different ways for getting the same answer. So there's the efficiency. There we go. We did the first 2 example problems. Now, let's get to entropy. We slide that desk in case I gotta. Actually, I think we're good. I think I remember dragging it through there already. You guys need a break, or are you good to keep going?
I'll go grab water. I'll be back in like 30 seconds.
All right, we'll take a quick break. Okay, that looks like it's back to going, not zooming on me. Find a piece of chalk. Small. A new one. Anyways, so now, yeah, let's touch on entropy and we'll give an actual definition of entropy. We've already talked about intuition for entropy. It's the amount of disorder or randomness in the system. We've given you, and also try to give you a notion of low entropy energy is in some sense more useful energy that's easier to get work out of. High entropy energy, not so much. So now let's get down to a definition. For a reversible process at some temperature T. Why are we saying a reversible process? It's always in thermal equilibrium, and so it always has a well-defined temperature. So at temperature T, then the infinitesimal change in energy, or the infinitesimal change in entropy, sorry, S is going to represent entropy here.
S is entropy.
S is entropy.
Okay.
Is going to be dq, some infinitesimal change in heat, divided by the temperature. Now let's try to get some intuition for this. If I've got a really cold system, adding a little bit of heat can drastically change how that system is behaving. Whereas if I've got a really hot system, adding that same amount of heat basically has no change to the system. In other words, let's take something like a glass of water. If I add enough heat to that really quick, then that's suddenly going to turn to steam, and that system changed a lot. Now say I go to the plasma on the surface of the sun, and I add the same amount of energy. What's the effect on the system?
Nothing.
Not nearly as much. And so, the amount of randomness, the higher the temperature is, the harder it is to increase the randomness in the system, the disorder in the system.
Direct correlation with temperature.
So,
that's heat.
yeah, it's related to temperature.
Oh.
So
temperature.
for some amount of dq heat you put into the system, here's how much entropy you increase the system by. How much disorder you added to the system. And so systems that already have a very high temperature are already really disordered systems. They're harder to disorder more. Whereas if it has a really low temperature, it's much easier to disorder the system with the same amount of energy. Just trying to give you some intuition for this equation, connecting it with disorder. Good so far? Okay. And now, if we're going to take some system now, and we're going to calculate the entropy as the temperature changes from some temperature beginning at T1 to some temperature T2, we're going to calculate that with this integral. This integral has to be along a reversible process, so that the temperature is defined all the way along there. And so that for each arbitrarily small change in temperature, or for each arbitrarily small amount of heat we add to the system, we can pretend for that teeny bit the temperature was basically constant.
So you can pull it out, is what you're looking at?
Well, no, not so you can pull it out, but we're just saying along each little step of our curve. So say our temperature is changing like this. Maybe I'll scribble it over here. Here's our temperature. We're kind of assuming for here it was basically constant, for here it was basically constant, for here it was basically constant. It's basically in thermal equilibrium all the way along Or in other words, our curve is continuous. There's no jumps in the temperature. There's no undefined temperature.
Then wouldn't it be
It's just
flat?
thermal equilibrium all the way along.
Would it be a flat line?
Now, we're saying it's really close
To flat?
to flat in every little step along the way.
That makes no sense.
It could change by an infinitesimal change dt. essentially what we're after is it's continuous. There's no jumping, and the temperature is always defined.
Yeah, it curves.
That's really what we care about. So that's why it's always along a reversible process. We get those changes. So where you do the temperature along some reversible path, then you can calculate the entropy this way.
Okay.
Good? So, if the temperature is a constant throughout the entire process, then you can pull the T out of the integral, and then it's just the heat added to the system divided by the temperature. Remember, Q is a change in energy added. So, when I integrate a dQ, then the final minus the initial is the change. It's the heat added. And so it's just Q. It doesn't make sense to do a Q1 minus Q2. You don't say your initial heat minus your final heat. Remember, heat is already energy transfer.
Okay.
Okay. Anyways, let's just do some examples because real easy to work with this. All right, here I am. I've got 1 kilogram of ice, and it's already at perfectly 0 degrees Celsius. I am just going to melt it. I'm going to add heat to the system until it melts, and I'm just going to melt all the ice.
What is your L?
So L is our heat of fusion. That's how much heat you have to add per kilogram of ice to get it to melt.
Heat of fusion?
Yeah, that's what it's called, heat of fusion.
Is that a common term?
Yeah, you had your heat of fusion that you looked up on a table, and your heat of vaporization that you looked up on a table.
Yeah, just
Your two
remember
different
the L
L's.
of P is heat of fusion.
L of
Okay.
F. That's an F.
Is it an F? I can't see. Oh,
Yeah, that's an F. Sorry.
Heat of fusion.
But how much heat do I have to add to 1 kilogram of ice to get to melt?
Okay.
Well, I have to add 3.34 times 10 to the 5 joules. That's how much joules of energy I have to add to get to melt. So, what's my change in entropy? It's just the heat, 3.34 times 10 to the 5,
Over your temperature.
divided by the temperature. What's our temperature?
Undefined.
What's our temperature?
Negative 273.
Positive 273.15.
It's 0.
Always in terms of Kelvin.
Oh. That's right.
Always in terms of Kelvin. And so that comes out to, we increase our entropy by, let's see, 3.34, this is example 5 in your book if you want to keep up that way, times 10 to the 5, divided by 273.15. And that gives us, we probably had, I'm guessing, 2 significant figures for the problem. So that's going to be 1,200, and entropy is joules per Kelvin, are the units on entropy. Because it's heat over temperature, joules per Kelvin. Good?
Yep.
Okay, let's do another entropy problem. This time, we got 1 kilogram of water. It's already melted, so now it's at 0 degrees Celsius. Basically, we took this water from the previous problem, and there we got it. Now it's all completely melted. And now I'm going to increase its temperature to 100 degrees Celsius.
Boiling point.
Yeah, get it up to boiling point, but we're not actually going to boil any water.
Oh.
Just get the boiling point.
Okay.
Heat capacity of water, we're going to assume is 4,190. Question is, what's the change in entropy?
4,190 divided by.
Which temperature do you use? Now the temperature is constantly changing. It's not a constant temperature. So first off, what is dQ?
The change.
Let's do Q really quick. What is Q? What's the amount of heat you have to add to do this?
0 to 100.
It's M times your heat capacity times your change in temperature, right?
That's right. I remember that.
Okay, so what's dQ? It's going to be M times C, those are both constants,
Yeah.
times an infinitesimal change in temperature.
dt.
With me? And now, how do you calculate entropy, or your change in entropy? Our change in entropy is equal to
dq minus.
the integral from, what's our starting temperature?
0.
Almost.
273.14.
And what's our ending temperature?
100.
373 Kelvin. And now we're doing dq over T. Pull out the MC, those are both constants.
dq over t.
And now, what's the integral of dt over T?
The integral of dt over t is the natural log of t.
Natural log of t. So now it's going to be the natural log of that minus the natural log of that. Or natural log of their quotient if you want to write it that way.
Okay.
And there's your change in entropy. So that all comes out to 4,190 times the natural log. Where's my natural log? Natural log of 373 divided by 273. Oops. 273. Comes out to two significant figures, it's 1,300 joules per Kelvin.
Your natural log is a function similar to cosine and sine, right?
Yeah. And there we go. There's our entropy in both those cases. Calculated it. Okay. Let's do another one. A gas expands adiabatically, so no heat is being added, and reversibly from V to 2V. So we double the volume of the gas. We didn't add any heat to the system. We did it in a completely reversible way.
So it gets cold.
What's the change in entropy of the system?
Volume.
The volume goes from V to 2V.
Volume.
So we know that our volume goes from V to 2V, but it's an adiabatic process, so our Q is 0.
So your T goes to, your T is divided by 2.
What's our definition of entropy?
The integral from 1 to 2 from the infinitesimal cubed over.
So how much entropy are we going to have in an adiabatic process as it expands from V1 to V2?
4.
From V.
3. It's 0.
From V to 2V. We're doubling the volume adiabatically.
0.
0. Why is it 0?
Because there's no heat.
Because there's no heat, so dq is 0. It's an adiabatic process. Not adding heat to the system, you can't change its entropy. Probably screams at something like 0 since I didn't leave any space for it.
It does not scream 0.
Oh.
It screams temperature.
Okay. Now let's try another one. Another trick problem for you.
No one can see.
Alright, here I've got some gas in half a container. With volume V is half that container. And I've got some dividing wall here. This is perfect vacuum over here. And I get rid of the divider so the gas can expand. First off, when the gas expands, does it do any work? No. Good, because there's no pressure. Okay. Our question now is, how do we calculate the change in entropy here? And now, there's something that I didn't emphasize like I should have. So let me emphasize something like I should have with our definition of entropy here. Since our definition of change of entropy here depends only upon the start and end position,
It doesn't matter the path.
then it doesn't care about the path in between it. It's what we call a state variable. Right? It's a state variable. And so it doesn't care about the path between it. Whatever the properties of the gas are dictate what the entropy is going to be inside the system. And so yeah, it doesn't care about the path that you take. So in going from V to 2V, what does this look like on a PV diagram? On a PV diagram, it's right here. Then we cut that string and it instantly jumps to right here.
But your pressure.
It did not take some path between it. It just went from here to here. Doop, dot like that. This is not a reversible process.
Yeah.
What is the temperature here? Let's say that the temperature here is T. Then what's the temperature over here?
2T.
It's still
Or
just T,
2T.
because the internal energy didn't change. The gas didn't do any work, so the internal energy did not change.
Your entropy changed.
Well, we're going to calculate our change in entropy. How are we going to calculate our change in entropy?
Your temperature and your heat.
I am going to pretend that this is what the gas did.
But
Even though it didn't do that, I'm going to pretend that this was a completely reversible isothermal process that went from here to here. Even though that's not what happened. You with me? And so now let's calculate that integral. So then delta S is equal to what?
The integral from point first point to second.
Well, we got to calculate this. What's dq? In an isothermal process, what's q?
Constant temperature, nRT, natural log, V.
Of your ending volume divided by your initial volume.
Okay.
Right?
Okay.
2.
So, I don't even think we need an integral for this one. Because our temperature is constant, so we don't need to do an integral.
Oh, you can pull it out.
So, yeah, so if you want to do the integral, you can say it's 1 over t times the integral of dq. If you want to plot the 1 over t, but the integral of dq is just q. And so it's just going to be q over t, where our q is equal to that thing. So it's going to be equal to n times r times t times 2v over v is just the natural log of 2. All over t, which cancels out. And so we get our change in entropy is equal to n times r times natural log of 2. There's our change in entropy in expanding the gas. And I don't care what that comes out to. Huh?
Those are all just constants.
Yeah, n is number of moles, so we're not changing the number of molecules. R is 8 point whatever it is.
8.3.
And natural log of 2 is natural log of 2. So yeah, we know what that number is. So there you go, there's our change in entropy. And so even though our system didn't take this path, we just pretended it did. Because it doesn't matter what path we pretend it takes.
So temperature doesn't matter, right?
Temperature matters. In this case, temperature was constant going from here to here. The temperature here and the temperature here are the same because it was free expansion. The gas didn't do any work.
So
No heat was added and the gas didn't do any work in going from here to here. We pretended that the gas did do work and that heat was added, which is a lie. That is not what happened.
Then how does our equation hold up?
Because entropy is a state variable. It does not care about the path you take. It just cares, here's where you were at the start, here's where you were at the end. I'm going to pretend that your gas did some work and that we added heat to the system. And the heat that we added to the system exactly canceled out the work that we did, so it's still all zero. And I'm going to pretend that the gas took this path even though it didn't. In reality, the gas was here, then it was there. And where it was in between is kind of hard to define. But it wasn't this nice smooth line, that's for sure. But we're going to pretend it was, because we don't care. We don't care the path you took. It's just like when I lift this chuck up into the air. If you calculate the change of potential energy, you don't care what path I took.
What's the end?
All you care about is where did it start and where did it end. Same with the entropy. Okay. Example 9. Using the Carnot engine from example 2 that we did over there, I wrote the numbers that we care about here. We had Q sub H was 2,000 joules. That's in one cycle. T sub H, 500 Kelvin. T sub C, 300 Kelvin. QC was 1,200. I can't believe I thought the exact same thing there. Okay. Find delta S.
That's funny.
So what is our change in entropy?
Integral. What is your 1 to 2 in that integral?
Sorry, what?
What is your 1 to 2? Temperature.
Here's our cool temperature, here's our hot temperature.
Which one's 1 or 2? Your hot is your 1. So 500 to 300 from your integral.
We're going to have to break this up, and we're going to have to break it up along its 4 paths. So I'm going to have my change in entropy going from, maybe write it like this. Here's probably the best way to do it. Should look that. Let's find delta S going from A to B. Delta S, going from B to C. Delta S going from C to D. And delta S
Going from D to A.
going from D to A. And then we can sum them all up, and that will be my total change in entropy. You with me? Your Carnot cycle has 4 processes to it. So I'm going to calculate your change in entropy going from A to B, then B to C, then C to D, then D to A. And that's one cycle.
Okay.
That's what we're calculating, is how much entropy is there in one cycle of your Carnot engine.
Interesting.
Say, so going from A to B, not sure how well you can see it there, what kind of process do we have going from A to B?
A to B, isothermal?
Isothermal process. So this is just going to be equal to, isothermal means the temperature is constant, so it's going to be equal to the heat coming in divided by the temperature of your heat source.
So just 1 over.
In this case, it's just QH over TH.
Yeah.
You with me?
Mm-hmm.
That's for the isothermal process, which in this concrete case comes out to, where are we at?
2000 divided by 500, which is
4
1/4.
4?
What? It's 400?
What are you saying? So
Oh, 40.
we're doing this divided by this, so you're doing 12 over
No,
5.
QH.
QH, 2000 divided by 500.
Oh, thank you. Okay, oh, that's just 4. So this is 4 joules per Kelvin are the units. Good. Okay, now what about going from B to C?
Adiabatic.
No, that one's adiabatic. We leave one isotherm, the TH line, and we go to the T sub C line. So that one is adiabatic, so what's our change in entropy?
0.
0, there is no heat. Okay, what about from C to D?
C to D.
C to D is isothermal.
Same thing.
Isothermal, and so
QH over TH, which is QC over TC. So it is your 1200 over 300.
which comes out to
4.
4. Or in this case, minus 4 joules per Kelvin.
Why? Because you're reversing it.
Because QC was the heat leaving the system. So how much heat is coming into the system? Negative 1200. So the change in entropy of the system is negative 4.
Okay.
It's always in terms of heat coming into the system.
Where do you get the original negative? Your
QC is how much heat is leaving the system.
leaving your QH.
Leaving your engine. Your engine takes in this heat from your hot source and releases this heat to your cold source.
Work is the stuff leaving the system. Oh, your
Both do.
both do. Okay, that makes sense.
What comes in, we don't have the work written up here, must go out. This and work go out.
So there's
Equals.
800 joules of work that goes.
So, what is the change in entropy in the system? It's the amount of energy you're adding, heat you're adding to the system divided by the temperature. So, if 12,000 joules are leaving the system, or 1,200 joules are leaving the system, how much are we adding to the system?
Negative.
Negative 1,200 joules, which is why it's going to be negative.
Okay.
And then finally, the last process is adiabatic for 0. And so the total change in entropy of our system is
0.
0.
Okay.
Which shouldn't be surprising because it was a cycle.
It was a trick question the whole time.
It was a trick question the whole time. But something important in actually seeing these numbers, the change in entropy to our environment is also 0. And so running a Carnot engine is the special type of engine you can run where you're not changing the entropy of the entire system, the entire universe, and it's staying 0, running a Carnot engine. When you run your engine, you are increasing the entropy in the world.
I can make a difference.
Okay. Now we got this cycle in our PV diagram, going from A to B back to A. Question, what's the change in entropy of that cycle?
0.
0. Good. And you could say it from saying it's a state variable, or the way that you could approximate this is you could represent this as get as infinitely many Carnot cycles as you want. Break it down, represent it as a Carnot cycle with a Carnot cycle, da 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 da.
What? When are you breaking into Carnot?
So I could break this cycle into, your book has a better picture of it, a Carnot cycle, a bunch of different smaller Carnot cycles to approximate the cycle. So I don't have to try and draw a bunch of them there.
That makes. I just don't get it.
Uh,
Bunch of Carnot. There's only that is a cycle.
Let's see a better picture from your book to help understand it. This one right here. Yep, that one right there. So I could break it up into, I don't know if I dare try and draw them, a bunch of mini Carnots. I can't draw the Carnot cycles. It's too hard. A bunch of little ones, but they're, they're those little elongated things. Because the Carnot cycle, I can pick any starting temperature I want, any ending temperature I want, and just make a little Carnot cycle using those temperatures, using that
So
piston.
why?
Well, the point is, in a Carnot cycle, the total change in entropy is going to be 0. And any other cycle you construct, I can approximate it with a bunch of arbitrarily small Carnot cycles. And it has to be the same as all those Carnot cycles, because it's a state variable. But you already got the idea with this coming out to 0, so you don't even...
No sense. I know.
It makes perfect sense. Read your book if you can, but we won't overstress it because you already got the main point. State variable, you go on a cycle, your change in entropy in your system is 0.
Yeah.
That does not mean that the change in entropy in your universe is 0. You could have still increased the entropy in the universe as a whole. Okay, so let's do another one. Calculating entropy. This time I'm going to have 1 kilogram of water at 100 degrees Celsius, 1 kilogram of water at 0 degrees Celsius. Now right now, think about how ordered that is. I got all this water exactly this temperature and all this water exactly this temperature separated from each other.
2 constants.
Now I'm going to dump the 2 waters and mix them together.
Divide 2 times. So 50 degrees Celsius.
So when it's all said and done, the water is going to end up 50 degrees Celsius when it all settles and reaches thermal equilibrium again. But what's the temperature in the meantime in between? Yeah, so we're going to pretend, you know, that we just gradually take just 2 little drops, decouple together exactly 50 degrees Celsius over and over and over again, keeping our system gradually trickling down, trickling up, whatever. Some way like that. Anyways, let's calculate the change in entropy now with this.
Alright.
So, our change in entropy, how are we going to calculate that?
Your Q.
For 1 kilogram of water, we're going to pretend that this kilogram of water, we in a completely reversible way, very gradually, incrementally decrease it down until it's 50 degrees Celsius. And for this cup of water, we're going to pretend that we gradually increment its temperature until it's exactly 50 degrees Celsius. And when they're both in perfect thermal equilibrium with each other, then we let them mix and whatever. So for this water, it always has a well-defined temperature as it slowly decreases to 50 degrees. And as this water, it always has a well-defined temperature as it gradually increases to 50 degrees. And we're not just going to dump the 2 waters together, even though that's what we do in reality. We're going to pretend with our math we did something different. So let's lie with our math and see what we get. So let's get the change in entropy for our hot cup. Now, our hot cup, is its entropy increasing or decreasing?
Decreasing.
Decreasing. It's going down. There's less jiggling. There's less randomness. So we better get a negative number here. And this is going to be the integral. What's our starting temperature?
373.
373. Or in other words, 100 degrees Celsius is what our starts out at. And what does our water end at?
273.
This is 373. It ends at what?
273.
No. What is the ending temperature of our water? It starts at 100 degrees Celsius and it's going to end 50 degrees Celsius. Or in other words, 323. You're close.
323.
Yeah, there you go. Okay, so there is our starting and ending temperature. Right? And we have, let's see, what is our dq going to be?
4090.
Maybe scribble it to the side really quick. If I just write it, maybe I'll scribble it. Oh, I think we already wrote it somewhere over here.
NRT.
I'll just scribble it again right here. You'll know when you see it. dq is just going to be equal to n times c times dt. For an arbitrarily little bit of q, there's our little bit of change in temperature.
So we can do the big void room.
So this is going to be equal to n times c times dt all over t.
You're right, you did write that somewhere before. So, problem 6.
Okay. Which is going to be equal to, pull out the n and the c, n times c times the natural log of, what's my top number?
What? Oh,
Exactly what we did over here.
of course.
Slightly different numbers. Good? And now this logarithm is going to be a negative number.
Yeah.
So this is going to be negative when we plug it into our calculator.
Why is it? It's leaving.
Remember that it's the log of this number minus the log of this number.
That's right.
Okay, now, so that's going to be some negative number. And then delta S from our cold source is going to be, it starts out at 273, or freezing point, and it ends at 50 degrees, which is 323. It ends at the same point that this water ends at, our second cup. And it's going to be the exact same integral. So dq over t, when we do it, we're still going to get n times c times the natural log of, this time, our top number is going to be 323, but our bottom number is going to be 273. You with me?
Mm-hmm.
Now, that is m, not n. M, not n. Sorry. Heat capacity is joules per kilogram.
Yeah, that's your
We're not talking about our C sub V.
What's your mass? 1 kilogram.
That is little c, not big C. Little c. Sorry about that. Did I make that mistake over here as well? No,
No,
over there I did it right. Okay, so. Good, didn't make that mistake before. Okay, so our mass we know is 1 kilogram. Our C we know is 4,190. And so now we can calculate this difference. So, we got 4,190 times the natural log of, I'll write this one first, 323 divided by 373. And that comes out to, so this first one comes out to negative 603 to 3 significant figures. This one comes out to, what do you think it's going to come out to?
I don't know what you're doing.
I just calculated this entropy. I just plugged that into my calculator.
Oh.
And that entropy came out to a negative number, which we knew it should.
How do you know your C?
So C for water. That was joules per Kelvin.
Let me guess, it's going to come out to 603.
Coming out to 603 would mean that the total entropy didn't change.
It did.
But it did change because the other one comes out to 704, or 705 when you round it, joules per Kelvin. And so having the two waters separated had less entropy than mixing them together. It was more ordered when they were separated than when they were mixed together. So our total change in entropy is the sum of those, and so our total change in entropy is that plus that comes out to 102.
Does that mean entropy is exponential?
Yeah.
It's not linear.
I don't know what you want to say in terms of that. It depends on whatever your process is. It changes with your process. But it's very much related to the temperature.
Oh, because you do it in Kelvin.
Okay, so
So the average two temperatures aren't necessarily halfway between, like 50.
Oh.
You good?
Yeah.
Okay. So now, there we go, entropy increased as we expected. Another way of stating the second law, now we have a definition of entropy, is entropy increases or remains constant when you consider the whole system.
Never.
Typically increases. There's no such thing as entropy going down.
Then how do we have low entropy? Wouldn't that over entropize?
We're not saying that there aren't systems with low entropy. We're just saying that when you have a system with low entropy, it doesn't go down. Entropy increases.
Entropy in the universe should be massive.
Entropy in the universe is much higher now than it was at the instant of the Big Bang.
And it forever. What happens
And it will
when-
forever to increase. And entropy will always increase in the universe.
What happens when it increases max?
Theoretically, I don't think that it can increase its max. As it currently stands, I think the universe is supposed to expand forever, getting it more and more dissipated. So I don't know if there's a theoretical max to what entropy can reach for the universe as a whole.
What does entropy even mean then?
Well, we gave you a couple things of what it means. Getting it good, I know exactly what entropy means. That's a hard thing to come by. One of the first guys to come up with the equation for entropy, when he came up with the equation, he was talking to, I want to say von Neumann, one of these great geniuses. He says, your equation, just call it entropy. Because even if you're wrong, no one will question you on it. So, entropy, pretend that you have some great deep understanding of entropy. It's kind of a hard thing to achieve.
What? It just doesn't make sense. What is
But,
it?
we'll try and give you some more.
Why can't we make it
I'm going to
ordered?
continue with trying to give you more what isn't. So now let's approach entropy now from a more microscopic view. And in this way, we are going to look at macroscopic states and microscopic states and look at the difference between them. For example, right here in this space, I can measure the temperature. Right? When I look at an individual atom, it doesn't make sense to say, what's the temperature of it? Temperature is a measure of the average kinetic energy of all the things in my gas.
Yeah.
So this is a macroscopic property versus velocity is a microscopic property.
Okay.
You with me?
Yeah.
And the velocities of this gas, the velocity of all the different molecules of the gas, can change into all sorts of different velocities with the temperature staying the same. I can have this gas moving with speed v1 and this gas moving with speed v2. And I can completely swap their velocities and it still is the same overall temperature.
Yeah.
So how many systems can I have that give me a temperature that I measure as, 40 degrees Celsius or whatever? How many different ways could I have the velocities of my gases arranged? They're not infinite, but a ton. So there's a difference between the microstate, the positions and the velocities of all our gases, versus the macrostates that we measure, like pressure, volume, and temperature. Intuitively, a state has higher entropy if there's more microstates that give you that macrostate.
So if there's more.
How many microstates give me a temperature of 0?
0.
Just one. That's one where they're, for our purposes, it's kind of a lie, but for our purposes, when is temperature 0? When all the velocities are perfectly 0 of the gas.
They're not moving.
And so when all of them aren't moving, that is the only way, that's the only velocity that corresponds to a temperature of 0. Whereas when we have a temperature of 100, now who knows how many ways? But a ton.
Exponential. Yeah.
And so, the more microstates you have for a particular macrostate, the higher the entropy of that state, or the more likely that state. It kind of relates to probabilities in this way. So I'll give you some of the book's language and then give you a hard example. The most probable macrostate is the one with the greatest number of microstates. Entropy captures the number of microstates. So your system, if it has more microstates for that macrostate, then it has higher entropy. So let's get very nitty-gritty, concrete example. Oh, let's move my camera first. And get a good feel for what I mean with just some coins. Something that we can easily wrap our heads around. Okay, so I've got 4 coins. Now, how can I have them arranged? And I've written them all out right here. HHHH, HHHT, all 16 possible combinations here. These are meant to correspond to your actual microstate of the system, knowing exactly how each individual coin is arranged. A macroscopic property would be like, this one has 4 heads, 3 heads, 2 heads, 1 head, 0 heads. How many ways are there for my system to have 4 heads?
1.
For this macrostate, there's only one corresponding microstate. How many ways are there for it to have 3 heads? 4. So for this one macrostate, there's 4 microstates. How many ways are there for it to have 2 heads?
6.
6. And so for this macrostate, there's this many microstates corresponding to it, etc., etc. Now say I've got some collection of 4 coins that I just occasionally are jiggling around. Odds are, if I were to stop at any given point, then it would be in a system like this, where we have 2 heads. So even if I started out with all 4 heads, if I randomly now shake it, it's going to tend to this kind of system.
Yeah.
Now that was just when we're talking about 4 coins. Imagine now if I had something like 10,000 coins. Then odds are, every time I shake it, it's going to increase. The system is going to change to one that has more and more microstates corresponding to it. And that's what we mean by increasing entropy. You can say this system has an entropy of 1, this system has an entropy of 4, this system has an entropy of 6, 4, 1. And you would be very shocked to have your coins in one of these configurations, and you shook it, and now it came out all tails. Now, it's not super surprising with just 4 coins, but now say you got 1,000 coins. And you have it all mixed up, whatever, and you shake it, and it comes out tails, 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 tails.
Not likely.
It's not likely at all. That would be entropy going down. That would be it going from a higher entropy system to a lower entropy system. We don't see that happening. We see systems going from a lower entropy to a higher entropy.
So it's impossible for it to go lower.
It's not impossible. It's just very, very, very unlikely. And so that is one thing you'll sometimes hear about the second law of thermodynamics, is that it is a statistical law, a probabilistic law. Because it's based on probabilities. Now, I'll give you a sense for those probabilities here in a second, but let's come up with one more definition now for entropy. This is the microstate version definition of entropy. Let W be the number of microstates for some macrostate. So if our macrostate is 2 heads in this system, then our W is 6. If our macrostate is, temperature of 50 degrees Celsius, pressure of 1 atmosphere, volume of 2 liters, how many possible configurations of our gases, different positions and velocities, would give us that pressure, temperature, and volume? A stupid large amount. And so W is typically a ridiculously large number.
Just infinite.
Not infinite, but just a ton.
Like, for a gas,
For a gas.
would be
Then there's a lot. And we'll leave it at a lot. The point is this W is going to be an absurdly large number.
which we don't need to calculate, right? How are we going to calculate that?
We'll see some.
There's-
I'll do a calculation with this W, I promise you. Well, you'll see. Just stick with me. Okay. So you got your intuition for W. It's a stupid large number. Let W be the number of microstates for some macrostate. Then we define entropy to be Boltzmann's constant times the natural log of whatever that W is.
What's Boltzmann's?
Where Boltzmann's constant is the R you know and love, the 8 point whatever, over Avogadro's number.
Which is 6.14.
6.022 times 10 to the 23, something like that.
Oh.
Stupid large number. In other words, Boltzmann's constant, regular number over stupid large number equals really small number.
It's not. It's only 6.
Times 10 to the 23.
6.
Oh.
Yes.
6.
It's how many molecules are in a mole.
Number. Oh, okay.
Yeah. So this is the actual number, whereas mole includes the units.
So K is small.
So K is a very small number. Yes.
You have to use a very big number.
Okay. Anyways, so now our change in entropy then is just your initial entropy minus
Your final.
final minus initial. W2 over W1. Right?
Yeah.
Okay, and there we are. So there's a definition. Let's now use this definition to calculate entropy in our free expansion system again. So I have my gas, it was in volume V, and now I cut the wire and now it doubles the volume. You with me?
Mm-hmm.
Now we didn't change the temperature, so we're not messing with any of the velocities. The velocities are whatever the velocities were before. Right?
Yeah.
By doubling the volume, what did I do?
Made less entropy.
I made so that for each molecule,
There's way more.
how many more positions does it have to be in than it did before?
A lot more.
How many more?
Twice.
Whatever.
Twice as many. So now for every single atom, it can be in twice as many positions as it was able to be in before. So let's say that W1, what's W1? How many configurations correspond to this state? I have no idea. Bonkers big. Exactly. So W1, bonkers big. That's what we know it is. But what is W2? Well now, for every atom, every molecule, big N, remember, is our number of molecules.
Big N.
That's a big N, sorry. I probably didn't enunciate well. Big N. Big N is our moles times Avogadro's number. Big N is actually how many molecules, count them. That's how many. That's what big N is. Okay. So big N is how many molecules we have. And for every single one of our molecules, it can now be in twice as many positions as it could before. So our first molecule has twice as many positions, times our second molecule has twice as many positions, times our third molecule has twice as many positions. And so whatever W1 was, when we cut that wire and we double your positions for every gas to occupy, W2 is now 2 to the N times W1. You with me?
Yeah.
And so now, what is our change in entropy? Using now this view of it. Our change in entropy is K times the natural log of your N minus over your start. So this is just equal to K times the natural log of our ending one, 2 big N to the W1, over our starting one, W1. Now, your W1s go out. Which is why, even though you're never going to figure out what that W is, you can still use this approach to calculate a change in entropy.
Because they go up.
Because they're going to go out. So W1 goes out. And so this is K times the natural log of 2 to the N. We went over some of our rules for exponents last time, but remind you, when you have an exponent in a log, you can bring that out front. And so this is also equal to big N times K times natural log of 2. With me?
Yeah.
What is Boltzmann's constant?
Some really small.
R over
Over
NA.
NA.
And this N can be written as N times NA, where little n times NA. So rewriting this like this, that's N times NA.
Over NA.
And rewriting Boltzmann's constant as R over NA.
Oh, NA squared.
Now, what happens to the NAs?
They cancel out.
They cancel out, and what are you left with?
R over N.
N times R times the natural log of 2.
What do I do?
I don't know. And, shocker of all shockers, gives you the exact same thing. So we already calculated the entropy one way, now we calculate the entropy using this definition of entropy. Still works, same thing. Good?
Yeah, makes sense.
Okay. Now, this is just saying that entropy tends towards the most likely system. Things just move towards whatever's the most likely. But what's to actually stop the reverse of that from happening? And all the air to just go back and occupy half the room? Why am I not trembling with fear that all the air in this room will suddenly just occupy half and we're going to suffocate? It's possible for that to happen. Why doesn't that happen?
Extremely unlikely.
Well, how extremely unlikely? If I stand here for a year, would it happen? 100 years, 1,000 years, a billion years?
Maybe a trillion.
Maybe a trillion? So 1 in a trillion years, someone drops dead of suffocation.
Yeah, probably.
Alright, so let's get a sense for just how unlikely that is. Okay, so the reverse of free expansion. We're going to say that the number of molecules in this room is roughly 6 times 10 to the 26.
Is that accurate or just saying?
It's okay approximation. Okay, so here's roughly how many molecules of air we have jiggling around in this room. What is the probability that we get the reverse of free expansion and they just occupy half the space? So pick some random molecule, call it Bob. Bob's whizzing around the room. What is the odds that Bob's on this half of the room?
50.
50%. And what are the odds that Jill's on this half of the room?
50.
50. And for each molecule, what are the odds that's on this half of the room?
50.
50. So the odds that all of them are on that half of the room are 1 half times 1 half times 1 half times 1 half, all the way to 6 times 10 to the 26.
That they're all just shifted over there.
That all the molecules end up on this half of the room. It's 1 half times 1 half times 1 half times 1 half for each of the 6 times 10 to the 26 molecules. You with me? Now, distribute that to the top and the bottom. 1 to whatever power, just 1. Put that in the bottom. Now, what's 2 to the 6?
12. Maybe 6.
You get closer.
4, and then 8, and then 64.
All the way up to 64?
It's 64. Okay, 2 to 6.
I actually got that right.
You actually got that right. Okay. What's bigger, 2 to the 64 or 10? Or sorry, 2 to the 6 or 10?
2, just
2 to the 6.
2 to 6.
2 to the 6, because that's 64. Okay. So, since we're dividing, then this number is for sure smaller than this number. You with me? I'm just giving you an easier one to think about. 10 to the 10 to the 26. It is less than a 1 over 10 to the 10 to the 26 odds that all the air will be in this half of the room. Now, trying to give you sense for how stupid small that number is almost impossible. So let me try. 10 to the 80 is roughly how many atoms there are in the observable universe. So we're going to play a game. I'm going to be some godlike being. Here's a game, and you're a godlike being. What I'm going to do is I'm going to look up at the night sky, I'm going to pick a random star, I teleport to it. And then I do that again 1 trillion times, teleporting to some random place in the observable universe. And once I'm in that random place, I'm then going to pick some random object. Maybe I pick the star right there, maybe I pick some little rock orbiting the star. And I go and I pick my little rock, and on that little rock, I'm going to pick a random atom. And I come back to Earth, I say, okay, I picked an atom, see if you can guess which one it is. What are the odds that you picked that atom?
10 to the 80?
1 over 10 to the 80, right?
Uh-huh.
And 10 to the 80, I mean, what is that? That's 1 with 80 zeros. I could easily just write that out right here. Won't take long. Right? Now let's say that we play the game again. You win. You pick that exact atom. Now I play the game again. And you do it again. 2 times in a row you do this. Now what are the odds of you doing that? 1 over 10 to the 60, or 160. And still, that's a small number in terms of I can easily write that number out. If I were to try to write this number out, it's going to have 10 to the 26 zeros.
Why is it 10 to the 26?
Because it's 10 to the 10 to the 26. This is not 10 to the 1026. This is 10 to the 10 to the 26.
I don't know.
Yeah, this is going to be a 1 with, or a 0.000. I got to write that 10 to the 26 times before I get my 1 there. Let's say I have super small handwriting. You think I could, how long would my string be if I were to write out this number? Let's get crazy with it. Let's say that I'm just lining up hydrogen atoms. That represents a 0. I use a 0 to represent a hydrogen atom. So hydrogen atom, and I finally write out that number. How long do you think that number would be?
The size of this board?
Probably the size of the board, somewhere in that ballpark. It would be the width of our solar system to write out the number. This number, write it out, no problem. We're not even close to big number compared to this number.
Going straight?
You can play our atom picking game and win it several times in a row before you come remotely close to how unlikely this number is. It is so ridiculously small. You can win the lottery many times in a row, well before you approach this number. It is so absurdly small. So it's hard for our brains to even appreciate. But
Yeah, it's so sad.
I have zero concern about suffocating.
I still fear it now that you said that. It's like,
But what if?
that's so dumb. Can you imagine dying from something as dumb as that?
No, I can't. Because I can't even imagine how dumb small that chance is. It's beyond my comprehension. These numbers are so small. I don't even know how to think about it. I have no intuition for how small that number is. Okay, so that ends entropy. And that ends the chapter. Now, if we have some extra time, I was going to get into another way that entropy often shows up
Shannon.
in what we call information theory. Sorry to you in advance. This is going to make more. Shannon is the last name of a guy who came up with this equation for entropy. So this is going to make more sense for Caleb and Alex, not so much for you, sorry, because it comes from probabilities and statistics. All right, so we've got some sample space and we've got some probability function. Let x of s be, it's going to be a real random variable, and it is going to be log base 2 of 1 over our probability. And this is called the surprise. Try and get some intuition for this. Imagine I have a coin and it comes up heads 100% of the time. Okay? What is the probability that it comes up heads?
100.
1. Or 100%, right?
Mm-hmm.
What's 1 divided by 1?
100.
1. And then what is the log of 1? 2 to what exponent gives us 1?
0.
0. And so this is called the surprise. If I had a coin that comes up heads 100% of the time, how surprised would you be if it came up heads?
0.
0 surprise. That's exactly how surprised you would be. On the other hand, what are the, say I got a coin and I flip heads 10 times in a row.
Normal coin?
Yeah, normal fair coin. Say I flip heads 10 times in a row. What are the odds I flip heads 10 times in a row? 1 in 1,024. Close to 1 in 1,000, right?
Mm-hmm.
So 1 over 1 in 1,000 is going to be 1,024. 2 to what exponent gives you 1,024? 10, that's how we came up with it.
Mm-hmm.
And so if you got heads 10 times in a row, how surprised would you be? You'd be 10 surprised. Okay? So for a coin that gives you heads 100% of the time, it came up heads, your surprise would be 0. On one coin flip, if it was a fair coin and it came up heads, how surprised would you be?
10.
No, just 1 heads. That's not very surprising. So that comes out to log base 2 of 2, which is going to be 1. So you're 1 surprised if it comes up heads, 1 surprised if it comes up tails. That's 50-50. And you're 10 surprised if you get heads 10 times in a row. Just trying to give you a little bit of intuition for how this kind of captures surprise and why that's what it's called. Okay, what's our definition of entropy? Our definition of entropy then is the expected value of surprise. Which, sorry, you haven't seen this function before. But it's just the probability of an outcome times whatever that function is, which is this function, which is that. So it's probability of some outcome times the surprise of that outcome, all summed up. And that's the definition of the entropy. Now, let's try and relate that to some concrete systems and actually calculate the entropy. So let's say I got a sample space where heads and tails are my 2 coins, and the probability of heads is 0.99999, basically 1, and the probability of tails is basically 0.
Mm-hmm.
What is the expected value then of x, where x is this function? It's going to be the probability of that function, which is, I wrote it as 1, instead of 0.99999, times log base 2 of 1 over 1. What's the log of 1? 2 to what exponent gives me 1?
0.
0. So this whole term is 0. And so, if we have this system where it's always and forever just heads, 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 it never comes up tails, then that is a 0 entropy system. That is as ordered as it gets. There is no randomness.
Mm-hmm.
Let's do our exact same system once again. And this time we're going to say it's a fair coin. So the probability of heads is 1/2, the probability of tails is 1/2. And we still have the same exact S that we had before, just heads and tails. Now let's calculate the expected value. What's the probability that we get heads? 1/2 times log base 2 of 1/2. Or log base 2 of 1 over 1/2. So it's always just going to flip the reciprocal up. So log base 2 of 2 is 1, 1/2 times 1. This comes out 1/2, this comes out 1/2. Total entropy is 1. So with a fair coin in the same system, your entropy is 1. If your probabilities were like this, then your entropy would be 0. And if I had a coin that came up heads 80% of the time and tails 20% of the time, then it'd be some number between 0 and 1. So 1 is the most disordered this particular system can get. 0 is the most ordered this particular system can get for these probabilities. And anywhere in between is going to give you some number between 0 and 1. Now let's move up to 2 coin flips. Moving up in the world, and from here on out we'll just use a fair coin.
Okay.
Using 2 coin flips, so we're doing S squared, where S is heads, tails, or in other words, flip the coin twice. The probability of any particular outcome is now just 1 in 4. Heads, 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 tails, tails, heads, tails, tails. So now, what's the expected value going to be? Well, it's going to be the odds of heads, heads, times log base 2 of 1 over the odds of heads, heads.
Mm-hmm.
Same with heads, tails, tails, heads, tails, tails. They're all the same, so it's just going to be 4 times. So that's why I'm just going to use fair coin from here on out, so that we can easily write out the math and don't have to write out a bunch of different terms. And what does this come out to? Log base 2 of 4 is 2.
Yep.
Times a fourth times 4 is just going to be 2.
Mm-hmm.
And so the entropy of that system is 2.
All right.
Let's move up and say that we have 4 coins. Well, the probability of each outcome, 16. How do we calculate the expected value? 16 times each of those 16 outcomes. The 16 and the 1 over 16 go out, and it ends up log base 2 of 16, or 4. And in general, if I'm flipping the coin n times, where the probability of each outcome is just 1 over n, then the expected value can be calculated this way, which is just log base 2 of n. Because 1 over n in the end keep canceling out. Notice that was happening every time.
Fire.
So that is the entropy of a system. Intuitively, if you were in information theory, we would measure the information of the system in bits. Why do we measure it in bits? Notice that each outcome I could encode with that many bits. If I just need to tell you heads or tails, how many bits do I need? A bit is a number that's either 0 or 1. I can tell you if I send you a 0, that means I flip the tails, and if I send you a 1, that means I flip the heads. And so I can communicate the system to you with 1 bit. So it's a 1-bit entropy system. It's how much information is in the system.
0 and 1, that's 2.
1 bit. A bit can either be 0 or 1. A bit is a number that's either 0 or 1.
Okay.
Now let's say I flip the coin twice. Then our possible outcomes are, if I were using bits to send to you, I can tell you 0, 0 means 2 tails. 0, 1 means tails followed by 0, 1 means tails followed by heads. 1, 0 means heads followed by tail. 1, 1 means heads followed by heads. And so with 2 bits, I can tell you what the system is. And so it's a 2-bit entropy system. There's 2 bits of entropy, or 2 bits of information in the system.
Why is that not 4?
There's 4 possible outcomes that I can have with 2 bits. A bit is a number that's either 0 or 1.
There's like 16.
Imagine I gave you 2. There's a reason why we relate this with coins and bits. Imagine I gave you 2 coins. How many different ways can you configure those 2 coins?
4.
4. So with 2 coins, you get 4 possible configurations. With 2 bits, you have 4 possible configurations. I can have those bits be 0, 0, 0, 1, 1, 0, or 1, 1.
But there's no 2 of anything.
This one has 2 bits. 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 I'm using 2 bits to tell you what happened.
2 bits by 4.
In other words, if I were sending you some electronic signal using a computer, I would need to send you 2 bits worth of information to tell you what happened. If I sent you 0, 0, you know it was tails, tails. If I sent you 0, 1, you know it was tails, heads. Just talking about like the regular binary that a computer uses. And so, for some system, if it were 16 coins, then the entropy would be 4, because I need 4 bits to encode all the possible ways 16 coins can be arranged. Which is one I have written out right here. I could do 1, 1, 1, 1 for this outcome, 1, 1, 1, 0 for that outcome, etc. Replace your heads with 1s and your tails with 0s. With 4 bits, I could tell you any of the 16 possible outcomes that occur. And so that system would have 16 bits of entropy. And that's how entropy shows up in information theory. So there's another way it shows up. So sometimes when you hear entropy, people relate it to the amount of information in a system.
Those are so vastly different.
They're really closely related. Because imagine that I were to tell you, forget this for a second, just say that we're playing a game here, and I've got a bunch of coins here. Heads, 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 heads. And these are all showing heads. Here's our game. Alex can't see these coins. But Alex has a bunch of coins sitting in front of him in the same configuration. So he just has 3 by 5 coins sitting in front of him in some random order. You can see this. He can't. You have to tell him how to organize his system to match mine. What would you tell him?
All heads.
All heads. Notice how easy that was to say. Now imagine I had some high entropy system where it was 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And it was heads, tails, heads, heads, tails, 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 heads, tails, heads, heads, tails, tails, heads, heads. Now tell him how to organize his coins.
0, 1, 0,
You can tell him in binary, you can tell him heads, tails, but it's way harder for you to tell him what's going on here than it is for you to tell him what's going on here. You can use a little bit of information or a little bit of communication to tell him about this system. You can't do it for this system. This is a low entropy system, this is a high entropy system. So there's another way of trying to connect it with your intuition.
Well, that makes sense. What's that got to do with those numbers?
This a little bit more for you to take in since you haven't done anything with
Bits?
Discrete math.
with discrete math in general. So there's a lot going on up here for you. So sorry about that. So that was meant more for the kids who had already done discrete math. But just connecting it, seeing how it's related. All we were doing with the entropy up here is measuring how much information was in a system.
What does that got to do?
It's how much information in a system is how hard it is to tell someone what the system is. It's really easy for you to tell someone what this system is. It's really hard for you to tell them what this system is.
Yeah, because it's
This system has low entropy. This is the case where it was like heads. The entropy of that system was basically 0. Where this one, the entropy of the system is not basically 0.
It's random.
It's way more random. Higher entropy takes more information to encode what the system is.
Oh.
It's harder to explain what it is. You talking to someone is you sending information the same way that you might send a binary zeros and ones. It's just a different language, a different encoding,
Yeah.
but you're still just sending information. So if it takes you a lot of information, then even if it came with some clever scheme on a computer, it would still likely take the computer a lot of information, and vice versa for a little bit.
Yeah.
Okay. Anyways, there we go. That's entropy. That's thermodynamics. That's physics 1. We're done with mechanics. There you go. You know physics.
No.
And now all we gotta do is get caught up on our homework and take our tests. So we'll have our chapter test. We have a little bit of wiggle room.
We should not take it.
We can either do, next week is our cushion week, the week after that's chapter test, or the week after that's midterm. Or we can do, next week is chapter test, then we get a week wiggle room, then we do midterm, or final. So, how do you guys want to do it? What do you want next week? You want test next week or cushion next week?
Cushion.
You want cushion next week? Do you care, Alex? Alright, we'll do cushion next week and assume that's what Caleb wanted.
Alright.
Yes, cushion.